Right, and hopefully everyone can hear me at this stage. Yes, I think it's working. Welcome everyone to the RQI circuit, the online edition of the RQI circuit. The goal of this is basically to give the opportunity to people that are not in big RQI hubs that can organize an in-person RQI circuit. So to present, so here we are. Our first speaker today is Ken Gallock. So please, Ken, go ahead. You feel free to share your screen, and hopefully people at home will also be able to hear you.
Hi. Can you guys hear me? Yeah. Right. And you guys can see my slides. Right. So, I'm Ken Gallock-Yoshimura from Kyushu University in Japan, and I'm going to talk about a quantum heat engine driven by quantum fields. So, this talk is based on my two recent papers, one of which is published in Frontiers, and the other is I posted online today, so you can go check out with this archive number. So this project is about something called a relativistic quantum auto engine. So to begin with, let's go to thermodynamics. And we all know that in thermodynamics, the main topics is the heat engine. So the famous one is the Carnot engine. And Carnot engine is the four-stroke heat engine with isothermal and adiabatic processes. Right? And you can extract work from this. Now, in recent years, people are very interested in combining thermodynamics with quantum mechanics. So if you do this, you get something called quantum thermodynamics. So for example, you have a qubit, and qubit might be immersed in a thermal bath, and you can examine how qubit extract work or exchange heat with the thermal bath. Now, also in quantum thermodynamics, you can consider something like quantum heat engines. For example, quantum Carnot engine and quantum auto engine are very popular engines. And in particular, quantum auto engine is our main topic here today. And this engine is basically four-stroke engine with two adiabatic and two isochoric processes. And it is very popular because you can compute heat and work in a separate manner. So it's very easier to analyze the exchange of energy. Right? So far, these engines are in the context of quantum thermodynamics, and typically people consider in the context of quantum mechanics. Now, one might ask, what happens if you introduce quantum field theory? And in this case, your qubit is now immersed in a quantum field. And this was first considered by these people in 2018, where they considered a qubit traveling in a space-time and interact with a quantum field. So your quantum field is now acting as a bath, and they show that you can extract positive work by using the induced Unruh effect. So by Unruh temperature, you can actually gain work from this. So in our project, we are basically considering qubit in quantum field theory and generalize this work in a sense that we are considering qubit's trajectory to be arbitrary time-like trajectory. So it doesn't have to be like a linear acceleration. And also field state can be arbitrary quasi-free, meaning it doesn't have to be Minkowski vacuum, but you can also think of like thermal state or quasi-free state, squeeze state. And also background space-time can be arbitrary globally hyperbolic space-time. So, like a black hole space-time and so on. So this is the general background idea of project. And before going to detailed results, I'd like to talk about the quantum auto engine. So in the mainstream quantum auto engine, people consider like qubit or harmonic oscillator. And in this case, let's consider qubit with energy gap omega 1. And the initial state is prepared to be something like this. Okay? Then you expand the energy gap to larger value omega 2. And in this process, you're considering like adiabatic process, meaning there will be no heat exchange between qubit and thermal bath. Now, you put the qubit into the thermal bath and thermalize with it so that in this process, um, the energy gap is fixed. So this can be considered as isochoric process, and the heat will transfer from the heat bath to qubit. Right? And you take out the qubit and again compress the energy gap to the original omega 1 value. And then you again immerse the qubit into the colder heat bath so that your qubit will release heat into the thermal bath until the point where the qubit state becomes the initial state, something like this. Okay. Then people showed that from this process, you can actually extract positive work. Okay. Now, in our paper, basically we want to extend this to quantum field theoretic point of view, in the sense that the heat bath is no longer just a heat bath, but it is a quantum field in an arbitrary quasi-free state. So it can be like a vacuum state, thermal state, or squeeze state, and so on. And trajectory can be anything. And also, it doesn't have to be like quasi-static process, meaning your interaction between qubit and quantum field can be like arbitrary time dependence. Okay? So this is our setting, which is very general. And here is a table of our result comparing to the traditional quantum auto engine. Okay? So in the traditional quantum auto engine, the assumptions were the qubit contacts with thermal bath, right? And also, the way they contact with the thermal bath is quasi-static processes, meaning they interact for sufficiently long time so that they can thermalize with it. Now, in our case, we're basically generalizing this assumption to something like this. So the qubit doesn't have to be interacting with the thermal bath, but instead it can be quantum field in arbitrary quasi-free state. Okay? So this includes the thermal bath, thermal state, and also the quasi-static processes is now instead considered to be a anytime dependent interaction. So it's like the time dependence of the coupling is arbitrary. And also, because we are considering quantum field theory, we are looking at global hyperbolic space-time and the trajectory of the qubit being like any time-like trajectory. And then we can compare the results. So the claim of the traditional quantum auto engine is that if you do that cycle and try to extract positive work, then the condition to obtain positive work takes this kind of form, where omega 1 and omega 2 are the energy gaps of the qubit when they are immersed in thermal bath at temperature Tc and Th, respectively. And if you compute the efficiency of the cycle, then it is known to be something like this. And if you substitute this condition, then this efficiency has the upper bound, which is equivalent to Carnot efficiency. So Otto cycle cannot go beyond Carnot efficiency as long as this traditional quantum Otto engine is concerned. Now, in our case, we can also consider positive work condition, and we can mathematically prove that the condition takes this kind of form, where my temperature is no longer actual temperature, but it is something called effective temperature observed by the qubit. So effective temperature is something like a fictitious temperature, and it is determined by the response functions, meaning response function is something like a transition probability between ground and excited states. And also, we can compute the efficiency of this cycle. And it turns out if you substitute this inequality here, then it is no longer Carnot efficiency, but instead, this can be considered to be generalized version of Carnot efficiency. So our setting gives very general results, and as a special case, it has the previous traditional results in the sense that if your quantum field is in thermal state and the qubit interact with the thermal state for a sufficiently long time, then your effective temperature becomes the actual temperature of the bath. So the previous traditional result is the special case of our result. So this is the main point in our paper. And finally, I want to talk about today's paper that I put online here. And previously, as I mentioned many times, our assumption is very general here, right? So like quantum field in arbitrary quasi-free state, global Habitable space-time, any timeline trajectory, and so on. Now, I didn't mention this before, but we used perturbative method, meaning I assume the coupling constant between qubit and the bath is very weak so that I can use Dyson series expansion. Okay. Now, instead of having these two assumptions, I can also consider something like instantaneous interaction. Okay? So everything before is the same, but the time dependence of interaction is considered to be like very quick. So this is like a Dirac delta kind of interaction. And it is interesting because instantaneous interaction in the context of quantum thermodynamics is very opposite of what people do, because usually people consider like sufficiently long time interaction, but we instead ask, what happens if I take instantaneous interaction? And also, by employing this interaction, I can use non-perturbative method, meaning I don't have to assume coupling constant is very weak. So intuitively, here is a spacetime diagram, and the two isochoric processes are now instantaneous. Okay? And we can ask, can we extract positive work with this kind of instantaneous interactions? And in this archive paper, we said yes, we can extract positive work as long as the first interaction affects the second interaction. So meaning here is a spacetime diagram, and when the qubit interact with the field for the first time, the qubit will disturb the quantum field. And this disturbance will propagate, for example, at the speed of light in Minkowski spacetime, for example. And my claim is that if the second interaction is affected by this disturbance of the field, then you can extract positive work. But otherwise, if the second interaction is not affected by this disturbance, then you cannot extract positive work out of it. So in summary, we considered quantum thermodynamics in the context of quantum field theory, and by assuming very general setting, we show that we can have very generalized version of traditional quantum auto engine, as well as very ridiculous setting but very interesting results with instantaneous interaction. So thank you very much for listening.
All right, perfect. Are there any questions for Ken? So you can just unmute yourself and raise your hands. Well, if not, I do have a question. So, Ken, you've been considering this coupling, which is basically the UDW coupling. I'm assuming, right? So you're coupling to the field itself,
Yes.
to the amplitude.
Yeah.
Now, what I was wondering is because if the field is in a KMS state, if the field is KMS with respect to the notion of time evolution of the detector, then whatever you get will be like whichever result you get will be independent of which field operator you couple to, simply because the KMS condition is satisfied, like as per its definition, right? The KMS condition is valid for all observables, for all operators, right? So it's a condition over the 2-point function. Have you, in your case, you're considering more general classes of states and of trajectories. You're not really only looking at the KMS, you're not imposing this KMS still. So have you looked up to
Yeah,
which
it doesn't.
extent your results depend on whether you couple to the field or to its momentum or to the derivative of the field or something like this? Have you explored this?
Oh, okay. Well, first of all, it doesn't have to be like KMS, in the sense that, like, if your Weidman function doesn't satisfy KMS condition, then, well, but still you can, do the same thing and calculate the positive work condition, right? In that case, it will be effective temperature, but there is no KMS temperature limit, uh, if you're asking something like that.
Yes, but then it's going to depend on many things, right? It's going to depend on which operator you couple to, on how long you couple for, on it's going to depend on
Exactly. Yeah.
on the energy gap. It's going to depend on a bunch of things, right? So basically, my
Yeah.
question is whether your results depend on, because you're varying the energy gap in order to implement these things, but does it depend on whether you couple to the field or to the momentum in this case?
Um, well, it definitely depends on, yeah, like the way we couple to the field. So the final, uh, yeah, but the point is, yeah, the actual value will depend on the coupling. But the point is, your positive work condition only cares about effective temperature. So, if that
Perfect.
answers your question.
Yeah, no, that's amazing. But you should definitely take a look at the whether this effective temperature depends on which field operator or observable you couple to. That'll be an interesting exploration, I
Okay,
guess.
sure.
All right,
Mhm.
cool. Thank you very much, Ken. So now our next speaker is Morgan Lynch. Morgan, are you here?
Oh, yes, I'm here. Can you hear me? Let me see if I can
No, don't
adjust
worry.
the
Zoom
volume.
adjusts this naturally, and we cannot see you either. So there's that point.
Yeah, I don't know what's going on with that. Like I have everything opened up here, but I guess as long as this is okay. Like I put on a nice shirt too, which is funny, but but I guess I
That's
won't be.
okay.
I guess you guys. Yeah, I don't know what's going on with my camera right now, but I can't. I don't know. I guess I don't have time to troubleshoot it. So
No worries. No worries. All right. Cool. So feel free to
okay.
screen share.
Let's see, how do I do this? Sure. Stuff on. Is that? Can you guys see my screen at least?
Yes. Hopefully
Okay.
soon. Actually, it's loading.
Is it good now?
It's still loading.
Oh my gosh. Okay. Maybe there's a big drag or something, but yeah, I don't know what's going on with my Zoom right now. I don't know why the video isn't working. Your screen share is loading. I don't know what's going on.
Do you want to stop and try again? Maybe it fixes the issue.
Yeah, sure. Let me stop and then share screen. That's funny. Now I see nothing. All right, let's see. You know, what's funny is because I'm actually at Max Planck right now, and they have their own kind of web web login here. So there might be an issue with that. If need be, I might get a hotspot on my cell phone. Yeah, now I can't even share screen. I'm not seeing anything.
Well, okay. So, how about this? Is Yanglin Hu here in the call yet? Was supposed to be the next speaker. Yeah. Then perhaps we can just switch the order.
Okay, cool. I'll try to troubleshoot these things. I'm sorry about the delay.
Perfect.
There.
No worries. No worries. Let's try to keep going, and then we're going to fit you whenever it makes sense.
Okay. All right. Thank you.
All right, sorry, amazing. Youngling, so you the screen sharing was working. The only question is whether do you want to have your camera on?
Yes, sure. I'm sharing the screen and turning the camera on. Oh, okay. Does this work now?
Yes, this is perfect. Thank you. Perfect. Amazing. So
Okay.
yeah, so you have 20 minutes, including questions. So feel free to use the time as you wish. Cool. So now our next speaker will then be Yanglin Hu, and they will talk about the feasibility of detecting quantum delocalization effects on on gravitational redshift in optical clocks. So please, Yanglin, the floor is yours.
Okay, thanks, Rick. Yes, today I'm going to talk on this feasibility of detecting quantum delocalization effects on gravitational redshift in optical clocks, and our paper has been on arXiv. This is a joint work with Maximilian Locke and Misha Woods. Okay, so here is the motivation of our work. Till now, several different quantum gravity theories have been proposed to unify quantum and gravity. And here are some examples that we are aware of. However, most of these examples are still in the theoretical stage, and we still expect more experiments to justify this theories by detecting quantum gravitational effect. Okay, and so recently, Kandelova and my other co-authors, they proposed a protocol that could potentially observe a discrepancy of relativistic time dilation between the quantum case and the classical case. And in their work, they consider a moving quantum clock with the clock and kinematic degrees of freedom in the low velocity and flat space limit. And for an idealized moving quantum clock, they consider this if this clock starts with a Gaussian wave packet in the kinematic degree of freedom, then the clock will output a measured time identical to the classical proper time. And if we consider the kinematic degree of freedom of the moving quantum clock is either in a spatial quantum superposition or in a spatial classical mixture of two Gaussian wave packages. And the wave packages, they have a displacement of delta x, and the probability to get one is lambda. And then after a free fall, there will be a discrepancy, T coherence between the time dilation of the quantum superposition, which is T superposition, and that of the classical mixture, which is T mixture. And the scale of this discrepancy is roughly 10 to the minus 16 seconds for 1 second of measuring time. And the state-of-art relative accuracy of an atomic clock is 10 to the minus 18. So that means the discrepancy is potentially detectable. However, the previous work by Tendelwa and my co-authors is based on free-falling clocks, and nowadays the most accurate atomic clocks are realized by confined atoms. So people may ask how to realize their protocol in a real experiment with a confined atomic clock, and does the noise do harm to the discrepancy? And this is what we want to answer in this work. We show that this discrepancy remains possibly detectable in a confined atomic clock model. And we also propose a method to realize a protocol and detect the discrepancy based on confined optical lattice clock. And we also analyze some possible noises such as amplitude damping, phase damping, and diffusion noise, and provide some feasible region on the noise parameter in order to detect this discrepancy. Okay, so we will go dive into our model. So our theoretical model is adapted from Zeich's model. We consider a point like we consider a point like particle with a clock degree of freedom, and we denote the clock degree of freedom by hc, and the kinematic degree of freedom we denote that freedom by k in this gravitational field. And this is the relativistic Hamiltonian in the laboratory frame, and we assume that the metric we are dealing with is static and the gravitational field is weak, so that we can apply the post-Newtonian approximation, which is given by this metric. And then we can expand the lab frame Hamiltonian in the low velocity and weak field limit. And furthermore, because our particle has an inner clock Hamiltonian, has an inner clock degree of freedom, so we can replace we can replace this MC square by MC square plus the Hamiltonian of the inner degree, and we can split the Hamiltonian into the kinematic Hamiltonian HK and the clock Hamiltonian HC. And we also assume that the atomic clock is subject to some potential U in the lab frame. So we furthermore add some U to our Hamiltonian. So as a result, we will get this Hamiltonian. Here we have written down all the terms that will contribute to our final result. Okay, so the evolution of the system and with dissipation considered can be analyzed by the Lindblad equation because the clock degrees of freedom have much longer lifetime than the kinematic degree of freedom in an atomic clock. We can consider the decoherence only via the kinematic degrees of freedom. And in that case, the equation can be solved by the perturbation theory. Here, this HC and HK in this red frame correspond to the unperturbed Hamiltonian of the clock and kinematic degree of freedom. And those terms in blue corresponds to the perturbative Hamiltonian. And the initial state, it is disentangled between the clock and kinematic degrees of freedom. But after evolution, because these blue terms, these freedoms will become entangled. So the kinematic part will come into the clock parts. Okay, so the clock degree of freedom of an atomic clock is usually described by a two-level system, and this atomic clock it works as follows. It compares the frequency omega naught of the atom transition and also the frequency of a very stable laser, and by stable the laser frequency to the atomic transition frequency, we can use the laser to generate very high quality time signals. And this comparison between those frequencies is via the Ramsey experiment usually. And these Ramsey experiments will produce the Ramsey fringes, which is shown on the right. So the laser frequency and the transition frequency, they coincide at the center of the fringe. And when the atom is still and in a flat space, and the contrast of the fringe is related to the accuracy of the experiment. So when the atom is moving in a curved space, by solving the Lindblad equation using the perturbation theory, we show that the relativistic effect will shift the center of the fringe and will also decrease the contrast of the fringes. So we compute this result by perturbation theory, and these are the lowest order shift up to the center frequency as a contrast. Okay, and now suppose we use two different atomic clocks. One prepares the spatial quantum superposition of two Gaussian states as the initial kinematic state of the clock, and another prepares the spatial classical mixture as the initial state. So these two clocks will give different results, and their difference is considered the discrepancy between the relativistic time dilation of the quantum superposition and the classical mixture. And now we give the discrepancy and the corresponding variance of the discrepancy of the atomic clock. And this frequency and variance are given by this delta, and this delta are given by the I1 and I2 parameter we given in the previous slide. So now we have the theoretical prediction for the shift and the variance. We consider the possibility to detect the discrepancy in an optical lattice clock. So an optical lattice clock relies on the optical potential to confine the atoms. The optical potential depends on the electronic state, and for a specific electronic state n, this optical potential will also is also a function of the polarizability alpha and the laser frequency omega and the polarization of the laser p. So a standing wave of the optical field will give a optical lattice, which is shown on the right-hand side of the figure. So for an optical lattice clock, these atoms are usually confined by very deep optical lattice aligned parallel to the gravity. And in this case, we can expand the optical potential near the balanced point and apply the harmonic oscillator approximation. So in that case, we will use the coherent state for the Gaussian states, because these are the most classical choice of the state, in the sense that they have non-negative Wigner function. And also this coherent state can be prepared rather easily by a displacement of the ground state. And now how do we prepare this coherent state or superposition of coherent states? Well, this can be resolved by the so-called state-dependent optical lattice. So consider we prepare the atom in a superposition of two different electronic states, and and these two electronic states are more sensitive to lasers with different polarizations. And in that case, we can displace we can use optical lattice formed by two standing waves with different polarizations, and we can displace these two optical lattices, and we will obtain a spatial superposition of the atom. This is shown by the picture on the right. So this method can be used to prepare the superposition and the mixture of the Gaussian states. Okay, now we introduce now we introduce our protocol more. So for timekeeping, an atom must have two very stable states, and this it has two very stable states, and the transition between these two very stable states are used for the frequency comparison. And for this reason, we usually consider, for example, the strontium 87 or magnesium 24 atoms. And in order to detect the discrepancy, we additionally need to prepare the quantum superposition or the classical mixture of two kinematic coherent states. And that needs a state-dependent optical lattice. And therefore, we have to require the atom to have some more energy structures. For example, energy structure like this. So in this diagram, the colors of the line indicates the wavelength of the transition, and the width of the lines indicates the strength of the transition. And we see, in addition to two very stable states for the clock transition, we also need two meta-stable states and two unstable states for the state-dependent optical lattice. Okay, so here is a summary of our protocol. So because usually the Ramsey experiment part is very well studied, so we mainly focus on how do we prepare the initial state. So we want to prepare either the quantum superposition of two coherent states, which corresponds to the left part, and this is the state we want to prepare, or we want to prepare the classical mixture of these two states, which corresponds to the right part of the protocol, and this is the state we want to prepare. Okay, now keep this two states in mind. I will explain how we prepare them each step, steps by step. So first, consider the atomic state is prepared in the very stable state S1. This can be achieved by the so-called spin polarization. And then we apply, we excite the state to the metastable state M1. And then we use a laser to induce the transition between these two metastable states, M1 and M2, and prepares a superposition of both states. Now we use these two states to perform the state-dependent optical lattice, and with the state-dependent optical lattice, we create an entangled state between the electronic state and the kinematic state. Okay, now if we want to get the spatial superposition, we again induce the transition between M1 and M2, and we will obtain this M1 alpha plus minus alpha and M2 alpha minus alpha state. Okay, so now we further excite the M1 state to the unstable state U1, which we get this state, and because this state is unstable, it will quickly decay to S1 spontaneously, and we obtain S1 alpha plus minus alpha state. And the M2 state will be abandoned by electron shelving. That is, we apply a laser to let it jump up to some unstable state, and it quickly fall back to itself and repeatedly. And the momentum it gains within this procedure will burst it out of the lattice, and we just clear it out of the lattice. And if we want to obtain the spatial mixture, we first excite this M1 state to this U1 state and wait for its decay. And then we excite this M2 state to this U1 state and wait for its decay again. And that will result in a mixture of this alpha and minus alpha state. And after we get the quantum superposition and the classical mixture, we induce the clock transition in the optical lattice. And then we we perform the Euro-Ramsey experiment. The measurement in the Ramsey experiment will be done by the electron shelving with this unstable state. Okay, so now in conclusion, we summarize our experimental protocol again. We first use spin polarization to prepare S1 state, and then transit it to M1 state, and then a Ramsey transition prepares the superposition of those two, and a state-dependent optical lattice prepares this state, and then if we want a superposition in the end, we will use a Ramsey transition again to prepare this state, and an electron shelving and spontaneous decay to get this state. Otherwise, if we want classical mixture, we again use the optical transition and spontaneous decay to get this state. And finally, we will perform the Euro-Ramsey experiment on those two states to obtain the Ramsey fringes and to get the frequency. Okay, so here is the energy diagram of magnesium-24, and I will explain how to use this atom. So in this case, this 1s0 and 3p0 state will be used as stable state. This 3p0 and 3p2 will be used as metastable state, and this 1p1 and 1p1 and this 3p1 are used as unstable states, and due to the overuse of 3p0 state, an additional cleaning procedure by electron shelving must be performed to clean this 3p0 state after the initial state preparation. And this transition will be used as the clock transition, and all the transitions between this p states are realized by Raman transition. Okay, and the spontaneous decay is realized by this transition. Okay, so this is how we achieve it with magnesium-24, and this is our numeric result for magnesium-24 state, which with magic wavelength and at 468 nanometers. So this blue line corresponds to the discrepancy versus the displacement between two Gaussian states, so it means we require a relative accuracy of 10 to the minus 19 to detect this discrepancy, and this red line corresponds to the contrast, to the decrease of the contrast versus the displacements between the two Gaussian states. And from this result, we see that the discrepancy remains large enough, while the decrease of the contrast is tolerable. So this discrepancy seems possible to be detected in the next generation optical lattice clock. And we also consider some decoherence. So we found that phase damping does no harm to our protocol. Sorry, so it's almost done. So I just say the conclusion. So as a conclusion, it's possible to conduct this real experiment, and our experiment seems to be robust against the noise. That's sorry for the delay. So this is our main conclusion.
Nice, amazing.
Thanks.
Thank you so much. Unfortunately, we're not gonna have time for questions. We're already running a little bit late, but thanks a lot for the presentation. All right, cool. So now we go back to Morgan. Now everything hopefully will be working.
Yeah, hopefully I'm keeping my fingers crossed here. I had to let's see, what is this even doing here? It looks like, look, can you see my screen? Oh, it's still loading.
It's loading, yes. But if you see it loading as well, then hopefully wait, it's gonna load eventually.
Okay. I don't know. I'm running on Linux, and so I think there's problems with this this Zoom that I'm using. But at least the video is working. Well, I'm trying to think. If this doesn't work, I'll have to think of something else to do.
Well, in any case, we do have the next speaker here. Sergio is here, so if you want to get some extra time to try to figure out for the next one, like we can push your talk once more.
Okay. I'll keep working. No problem. I apologize for this, but thank you very much.
No worries. All right.
All right.
So,
Stop sharing all this.
Sergio, are you available right now to start your talk? That would be nice. Amazing.
Can you hear me?
Yes, I can hear you. Can you start screen sharing?
Yeah, just let me check for the presentation. Okay.
Yeah, sorry about that. It's just that otherwise we would be wasting some time just waiting for technical issues to be fixed.
Yeah, it's always a challenge in these Zoom meetings. Okay. Yeah, the presentation is still loading, so let me check. Okay. Now I can share the screen, but yeah. Yeah, you can see, right?
Yes, we can see it. If you want to put it on full screen.
Sure. Should work. Is it better?
Yes, perfect. Amazing. So
Okay.
now for the next speaker, we have Sergio Ernesto Aguilar Gutierrez, and he'll talk about entangled universes in the sitter wedge holography. So Sergio, please, the floor is yours.
Yeah, thanks a lot. Thanks, Thales or Nick. But yeah, this I also added a bit extra about the complexity in this model, because yeah, I'll present something about some previous paper that also was used in order to complete the whole story about the quantum information properties of this wedge holographic model. Okay, so it was done in collaboration with Juan Pedraza, with Ian Kumar, and in this the main paper that I'll tell you about, I'll say something else about the complexity in the sitter that we did with Michael Heller, Silke van der Schuren, and also some recent work with Philip Langland. Okay, but of course, if I only have 20 minutes or a bit less because of questions, then I'll mostly focus on the first paper. Well, this is about the wedge holography. So what do we mean by that? Usually these are like double holographic models where you have some higher dimensional spacetime that is well, there are different implementations. The main implementation was with the way that Takanagi and other people initially proposed this type of models. That is, well, that is also based on the standard Garch-Randall models. That you have some higher dimensional ADS space, and then you have some end of the world brains where you can have some type of theories. The modification with wedge holography is that then now they are like a pairs of brains where the intersection between the two brains will be something that is like a double holographic. It has like a codimension 2 quantum theory that has been implemented in different contexts. The one that we are focusing in this DS wedge holography is when you have some the zeta end of the warp branes, and there is some intermediate ADS space in her dimensions that is between the two. Sorry, that is in between the two branes, and there is like a location that is in the intersection between the two branes. They are basically some accelerating universes from the brane perspective or from the high-dimensional point of view. Here we have just the Poincaredis, the cylinder, where you can have that these branes will start at some given starting location that in global ADS coordinates is just at minus pi half, and then it evolves all the way to some other location where from the brane perspective is that basically it's from going from minus past infinity to future infinity from some brane observers. Okay, so that's basically the setup. The idea of wedge holography in our case is basically that we have two ends of the warp branes. One is the UV brane, and the other one is the IR. By UV, I mean that it's very close to the UV boundary, and by IR, it's just it's deep in the bulk interior. And the region in between is what we call the wedge. Okay, so this is the type of model that we're considering. This is just instant gravity. We consider that this, from the higher dimensional point of view, there is a negative cosmological constant, and we have some pairs end of the warp branes with some given tension that will be determining the location of the branes. There are two main cases that we consider in this paper. One where these branes are like in any dimensions, and you basically fix them at some particular location that is just given by the tension of the branes. And there is another that I'll explain you later, where we actually let the brane location to fluctuate. And in that way, we do need to go to lower dimensions in order to get some analytic expressions for quantities that we're interested in. So in this case, we were using these global ADS coordinates, where we have some de Sitter foliations for ADS, and basically this we can delimitate the location of the bulk in the wedge holographic model between the UV and the IR that we presented with subindex C and V in this particular way. Basically, this you can think about this from the perspective of some Euclidean path integral implementation of preparing a state for creating this type of configuration in the bulk. Okay, usually you would like to put some operator in the UV boundary and then in the Euclidean ADS, and in that way you can create some states that they can propagate into the bulk, and in that way you can create some type of states. But in this type of Hartekokian type of preparation of a state, you can clearly see that the UV brane that is in the right one, and the IR that is this orange will not reach the boundary, so they need to be created by some non-perturbative type of process. In this case, it's just some instanton creation of EPR type of branes. This is how you can think about the preparation of this configuration. And then there is another point that we want to study some information quantities in this type of setting. So we're basically going to take that one of the branes, the UV, will be very close to the boundary. In that case, then the theory basically becomes gravity becomes basically non-dynamical, and then one can study these information theoretic properties without having to worry about some non-local gauge invariant type of observables. Now you have like a much more control, And we also had some arguments about how this can be taught about some momentum space entanglement between the UV and the IR that actually tells you, based on some previous works, that this will mean that basically you have some factorization between the UV and the IR that will be like the modes that are like encoded between the two type of brains, and then the Hilbert space factorizes, and then one can study sharply about these notions of holographic entanglement entropies or holographic complexity in these cases. So to study that was the setting. Now we want to focus on what we can learn about this in order to get some lessons for the de Sitter holography, basically from the ADS perspective. So we can use this HRT formula that basically tells you about how to relate some entropies in terms of some quantum dual to some gravitating theory. And well, first we specify what type of entangling region we want to consider, where we can do the measurements of some quantities. So we specify this R using this de Sitter global coordinates for the embedding that we have, like ADS that they can be foliated into the de Sitter slices. Here we are using that this R has to be some global. Well, it's actually okay. This is a typo. Here I'm using the de Sitter slices and using this global de Sitter time instead of the global ADS that I was using in the other slices. Then this R is basically just some interval. This is for convenience. This makes the calculation basically much easier. I'll show you how this looks in some pictures. It's just some intervals in this type of foliations. This is like the some maximal and minimal values for the angles, and then we're looking at different global time slices. Then we can think about this is basically some observer that is in the UV on the UV plane. Then this is the natural coordinate system that they will be measuring in global de Sitter coordinates. And then we can think about these HRT formulas, how we can implement these notions of entropies in respect to this UV observer that is close to the boundary, using just some geometric notions in the bulk, using some dimension 2 surface areas that are like homologous to R. So this is basically how they look like. Again, this is a typo, sorry about that. But yeah. No, this is fine. So here we have some foliations. Well, some global time slices in global ADS, where you can see about the locations of the different brains. Yeah. So we're basically fixing that this region in black, there is R, will be the entangling region where we put we're making the measurements. When we are like computing the entanglement entropy for some reduced density matrix in R from this whole slice that is in the UV brane. And basically here we can have different type of phases for the entanglement. One will be like some surface that here we are calling it disconnected because it is like only connecting the UV, but it doesn't connect the UV with the IR. And there is also some connected phase that basically goes from the just from the quasi boundary to the location of the IR brane, where we are integrating out some degrees of freedom. So basically, these are like the two cases. There is another one where this interval R is large enough that it basically also covers some region in the interior of the IR brane. When that happens, then you also need to take into account that then there is like some maximal number of degrees of freedom encoded in this IR brane, and that has to be implemented also when you're doing the calculation of the maximal area surfaces. Then if you have like a multiple saddles, because now you have like a disconnected and a connected phases, then basically the entropy that will dominate in the calculation is the one that is given by the minimal between the two cases. Then this is what you can find about the notion of a Pesch curve. Obviously, here I skip some details about how you can do this calculation, but yeah, in principle, is very straightforward. Here I'm just plotting the different entropies you can find. This is for simplicity in the three-dimensional case that you can recover this plot. You can in principle recover something very similar when you're talking about the hard-dimensional cases, and then there is some phase transition at some particular time. Basically, you can find that this phase transition is always occurs before the disconnected phase actually reaches the IR branes. And then there is an interpretation that now we can see that there is some island phase that is basically the one that is connecting the two branes, that they will represent some connection between the UV and the IR locations of the modes. And this is also related to some previous work about the momentum space entanglement between different spaces okay. In principle, was used in some free theories, but it also has some generalization with the interacting mass. Okay, this is the second part of the talk that is about the complexity. Basically, we study like a different codimension one type of observables that we're calling that there are like many hints that they may have some representation from complexity of some quantum circuit that might be dual to some other notion of that we're calling like a holographic complexity in the bulk. And then this is the particular type of observables that we studied in this case. This is called the equal to anything proposal for codimension one observables, where this sigma epsilon, where this epsilon, I'll show you how does it look like. Basically, are surfaces where you're evaluating complexity. Okay, great. And then there is like some particular region of where you are like fixing these two slices. They represent basically the future in the past of some particular slice. Here you can see how this looks like. Basically, here we have the UV and the IR branes, and in between we have the global ADS. There is some bulk region that is delimited in the past and the future by these two slices. And basically, we want to define this location of these particular slices using the extremization of some function. In that way, you can have a covariant notion of some observable. And you can find that the extremization for this type of sum of weights of different codimension 0 and codimension 0 and codimension 1 volumes basically tell you that the extrinsic curvature of these slices has to be some constant that is given by the particular weights that we're using. Okay, so this evaluation is in principle very complicated if we are talking about the particular case that we consider. Basically, you need to use some coordinate system where you can do the explicit evaluation, and it becomes tractable. But yeah, for this wedge holographic method, it's still cumbersome. Then the simplest case that I'll present you, but you can see, of course, more details how this gets more involved in our publication. The case I'll tell you is about when the IR and the UV are close to each other, and basically that's where you have just they're basically just considering complexity in the de Sitter slice, in the de Sitter brane. So you're not worried about some corrections due to the intermediate bulk space. Okay. Yeah. So. This is also based on some, well, this pair is based on some previous work on the Sitter complexity. that I'll tell you a bit more about. But basically, you can find that there is like some using this type of codimension one observables, you can see that the evolution of complexity basically obeys this type of evolution. It goes from some point where this some rapid growth of complexity according to that type of observables that as you increase like the the mean curvature of these slices, this growth can be layer in layer, basically because of how geometrically you can see how this is implemented in that case. Then you can also study what happens when you increase the values of this mean curvature. There is a point where this actually, instead of reaching some hyperfast growth of complexity, basically when the derivative goes to infinity, there is instead some critical value of the mean curvature where this slices simply where the complexity simply grows linearly with time. And then you can derive some relation for that. I can tell you some technical details if anyone is interested. And then we also propose some way that we can implement some covariant notion of this linear growth of complexity, that you also have some expectation based on quantum circuits. And then here you can see our work where this was first proposed, and we also applied this in the wedge holographic method. So this is just to wrap up. Well, I'll tell you very briefly about this. You can also study what happens when you let the brain fluctuation to the brain location to fluctuate with some scalar modes, and then you can find that the higher dimensional from 3D gravity in the bulk, you can see that the two-dimensional effective description of these fluctuations is described by the zeta JT gravity. We also propose some multivariate model based on the lower dimensional cases, and this was with Philip. That was that I can explain you what we mean actually with that. But yeah, since I see we are running out of time, then I'll just give you some brief summary. Then we studied this notion for testing quantum information concepts in the zeta space with the ADS-CFT dictionary. We studied that there is an emergence of island phase transitions between the UV and the IR. There is this notion of complexity proposals where some of them has hyperfast growth and some of them has latent linear growth. And then there are other interesting application for lower dimensional gravity that you can study. Okay, thanks you.
All right. Thanks, Sergio. Thanks a lot for the talk. If there's one question from anyone here in the Zoom meeting, then perhaps we have time for one question. If there are none, I can ask you a short question then. It's so when people usually talk about complexity, the way that I think of it is that complexity is basically this amount of basic operations that you need in order to implement a task, right? So in this case, when you compute the complexity, what is the meaning in terms of this more mundane view of complexity of basic operations?
Yeah, precisely. From the gravitational side, and we have also some expectation that as you increase like the volume or some length of a wormhole inside a black hole, this has some representation in the field-theoretic dual to be also like implementing like a higher number of states or gate counting that you will need in order to implement some number of operation in order to reach from some preparation state to some target state in the circuit dual. It's exactly that the motivation for all these complexity notions in the ADS case that they were also implemented in the de Sitter case. Latent growth, that's one of the expectations, and also the switchback effect. Those are like the two ways to do requirements in order to define these observables.
Nice, amazing. Sergio, thanks a lot. Let's thank Sergio again. And now what we're going to do is we're going to give Morgan one more talk to get ready with his Zoom. And now we were supposed to have a talk by Navdeep Arya. However, they have contacted me a couple of days ago, and they will be unable to deliver this talk. But David Kubiznak was kind enough to offer himself to deliver a talk this time. So, David, do you want to show your camera and mute yourself?
Hi there, can you see the screen, please?
Yes, we can see it, but it's not on full screen. Do you want to put it on full screen?
Is it now?
Now it is. It's perfect. Yes. Amazing.
Perfect. Okay. Well,
All
thank you
right.
so much for this opportunity. And so I will tell you about Bekenstein's area law. And there's a common wisdom that maybe Bekenstein's area law for the black hole entropy should be modified once you go beyond Einstein gravity. And so the aim of this talk is to actually tell you that maybe this is not the whole story, and maybe the story is a little bit more complicated. So what we laugh about the Bekenstein's area law is the following formula, and I would think that this is one of the most beautiful formulas in theoretical physics. And one of the reasons is that basically it combines all of theoretical physics. So it combines relativity, where you have the constant c. It combines the statistical physics because you have the Boltzmann constant in there. It combines quantum mechanics with gravity. So it's very, very, very beautiful. And moreover, it has very intuitive meaning. So if you actually introduce the Planck scale, as done over here, then you will see that your entropy formula rewrites as basically you measure the area of the black hole horizon in these Planck units square. And so that precisely tells you, like, yeah, I divide my horizon into small pieces, and how many of those pieces I have, that gives me the black hole entropy. Moreover, this formula is holographic, meaning that actually you would typically think that the entropy of a system should scale as the volume of the system. However, this is not the case for black holes. It actually scales rather as the area associated with the surrounding boundary of the region. But as I told you, the accepted wisdom is that no matter how beautiful this formula is, it will get corrected once you consider high curvature corrections to Einstein gravity. And so there's a magic formula for how to calculate this entropy, and it's given by Walt's prescription. And what basically Walt showed you is that you can calculate the black hole entropy by calculating some local quantity associated, evaluated on the horizon, the black hole. You integrate that, and then you get the entropy. And what is amazing is that this quantity Q here is actually not a charge associated with the Killing vector, which is the horizon generator. And so this prescription actually gives you, for Einstein gravity, precisely, it gives you the area law as prescribed by Bekenstein. But if you consider standard high curvature gravities, it will give you something a little bit different. So let me give you an example. So let me consider the simplest possible, if you want, modification of Einstein gravity. So the action now is the Einstein-Hilbert action plus a Gauss-Bonnet term. So what a Gauss-Bonnet term is doing is that basically it's a quadratic in the curvature term, and the coefficients of these quadratic terms are precisely tuned. So you have really 1 times Riemann square minus 4 times Ricci square plus 1 times Ricci scalar square. And so there's something magic about this specific combination, is that although it seems that your Lagrangian contains second order derivatives of the metric, it still yields the second order equations of motion. So anyway, so now you may be interested, like what the Wald prescription gives you for this theory. And interestingly, if you are in dimensions greater than 4, it gives you modification of the Bekenstein's area law. It gives you area over 4, plus you have to integrate the Ricci scalar. This is the determinant of the metric on the horizon. But there is a correction due to the Ricci scalar on the horizon. So you no longer have Bekenstein's area law. However, even more interesting story actually happens in 4 dimensions. So in 4 dimensions, you can show that this Gauss-Bonnet term here is actually topological. It means it's like a boundary term. And so if you have a boundary term adding to the action, it doesn't affect the equations of motion. So basically, this action in 4 dimensions still yields the standard Einstein equations. However, what you can show is that the entropy actually gets modified if you add this topological term, and that's been known from the end of 90s, from 90s. And in fact, the shift in the entropy is proportional. So say it's given time alpha, which is the coupling constant of my Gauss-Bonnet term, times the Euler characteristic of your manifold. So basically, that counts how many holes your manifold has, and it's a constant for a given manifold, unless you change the topology and stuff like that. And so there's a constant shift in the entropy due to this Gauss-Bonnet term. However, this actually raises an interesting question. So let's say you collide 2 black holes and you start with a manifold with 2 holes, and then you collide them and you form 1 black hole, and so suddenly you have only 1 hole in your manifold. And in this way, in principle, this term will contribute in such a way that you can make, you can tune alpha so that your entropy in this process will actually decrease. And so this gives a possibility of violating the second law of thermodynamics. Anyway, so this is the truth. So now what we can do is that we can go. So this was like a sort of trivial for the Gauss-Bonnet gravity, but you can formulate another one, which is like obtained by a singular limit of the higher dimensional Gauss-Bonnet gravity. So what do you do is that you start with your higher dimensional Gauss-Bonnet gravity, and then you introduce a conformally rescale metric. So you rescale the metric by e to minus 2 phi, where phi is some scalar field. Of course, at this point, this is just a change of variables. There is nothing new here. And so you plug this into your Gauss-Bonnet action and in your Gauss-Bonnet term. And then what you do is that you expand around 4 dimensions. So you expand in epsilon, which is d minus 4. Okay, so now you have the following expansion. You have the absolute term, and then you have linear term in epsilon, and then you have quadratic terms, and so on. So we already know that the absolute term is precisely what we were obtaining by naive limit d goes to 4. So we obtain a topological Gauss-Bonnet term, which does not affect equations of motion. So that's not interesting. But then you may be after the second term in the expansion, and you can call, well, why don't I take the second term to be my new theory of Gauss-Bonnet gravity in 4 dimensions? Of course, in order to do that, you have to rescale the coupling constant alpha hat epsilon to alpha, and then this term really becomes finite, and that's what you will call a new theory. At the same time, of course, the absolute term blows up, but you can kill that by adding the corresponding counter term if you want to. Or you can just say it's still topological, no matter that it's multiplied by infinity and zero it away. All right, so this is the resultant theory. And if you look at the theory, it has the scalar degree of freedom. So now you have suddenly scalar tensor theory of gravity in 4 dimensions, where you have the phi scalar field, you have still the Gauss-Bonnet term over here, and then you have some very specific and ugly kinetic terms for the scalar field here. All right, and so people have studied what happens to black holes in this theory. And if you naively apply the Wald prescription for the entropy, you will find that, again, the area law is modified, and it's modified by the value of the scalar field on the horizon. The scalar field on the horizon, so the scalar field in the space-time, spherically symmetric space-time, black hole space-time, it behaves like logarithm of R over L. So, of course, if you evaluate that on the horizon, it gives you a logarithm R plus over L correction to the area law entropy. And what remains here is the standard integral over the Gauss-Bonnet term, so it gives you a constant. Okay, so it's basically scalar field on the horizon times a constant coming from the Euler characteristic of the manifold. But this is a very exciting result, and many people were super excited about it, because now you have basically classical field theory, which gives you logarithmic corrections to the entropy, which typically are considered like quantum effects, right? So you get typically logarithmic corrections to entropy at the quantum level, but here you are just getting it from a classical solution of a classical field theory. And so people were very excited about that, and they said, well, this is like the right Lagrangian to play with if you want to capture some quantum corrections and so on. Anyway, what we are trying to say is that this is actually not completely correct. And the reason why this is not correct is that the theory which you have here is shift symmetric. Meaning, if I take my scalar field and change it by adding a constant, then of course what happens that all these kinetic terms here, they vanish because they just kill the constant. But here I have the original scalar field plus constant times g. Okay, but we know that constant times g is topological. It doesn't affect the equations of motion. So really, we have classical shift symmetry for this Lagrangian, and so we have to have exactly the same classical solutions. But what happens is that we already know that if we add constant times g, that modifies the entropy. It shifts the entropy by a constant. So you have classical symmetry, which, however, affects a physical quantity like the entropy. So that seems very, very strange. And so we thought, why don't we make this shift symmetry, which is true for the equations of motion, already manifest at the level of the action? And to that, you notice that really your Gauss-Bonnet term is like a total divergence of something. And so what you can do is that you can take this action here, write the g as nabla mu g mu, and you can integrate by parts, sort of, by adding this boundary term over here. So what happens is that basically it shifts the derivative from nabla mu g mu to the derivative of, so this should be the scalar field phi, plus the remaining kinetic terms which are over here. So this is the scalar field phi. So now you see that this action is manifestly symmetric, shift symmetric, because now I am differentiating my scalar field, which is not visible here, and then I have kinetic terms. So really the action already manifests this shift symmetry. Very good. And at the same time, it leads to the same equations of motion, because all we have done is that we have added a boundary term. So this is your action, and now we can again use wall prescription for the entropy. And surprise, surprise, what you will find is that the logarithmic term suddenly disappears, and it just recover the Bekenstein's area law. So of course, there's a price to pay for this, and if you want your first law to be satisfied, and the mass does not change, and you want still dm equals to TdS, you have to modify the temperature. And this is the corresponding modification of the temperature. So this is the Hawking temperature, and this is the factor I have to multiply my Hawking temperature to get the temperature which satisfies the first law. Okay, so this was true for this 4D Gauss-Bonnet gravity, but what about the pure Gauss-Bonnet gravity, let's say in 5 dimensions? No scalar field. Well, in 4D, I was trying to tell you that the Gauss-Bonnet term can be written as a total divergence of something. Unfortunately, or fortunately, or maybe there's a reason for that, there is no covariant expression known for this G mu. So typically this G mu can be explicitly defined in terms of the Christoffel symbols and stuff like that, but that's not a covariant expression. However, if you have a killing vector in your spacetime, let's say psi mu, then there is a covariant expression due to Patmanabhan. And so you just take the Gauss-Bonnet term, you differentiate with the Riemann tensor, and then you take this combination of the killing vector and the d of killing vector, and that gives you the G mu. That's the prescription for this G mu. So that's a prescription for 4D, right? But why don't I use the same prescription for 5D? It's just an educated guess. So why don't I consider the 5-dimensional Gauss-Bonnet gravity, which definitely leads to modified entropy, and then add this boundary term to it, okay? And if you do that and turn on the machine again, you find that the wall entropy formula gives you suddenly area over 4. It kills the modification of the entropy. Again, you have to modify the temperature. So where does this temperature come from? Or is there a way to derive this modified temperature? And yes, there is. It's almost the standard Euclidean path integral formulation. It's a little bit twisted by Brown and York, and I can give you a reference if you are interested in. But basically, there is a Euclidean action calculation which allows you to derive the temperature of the space-time, and it precisely gives you this modified temperature, and it gives you this modified entropy. So you may be asking, like, why the temperature should be modified, right? It shouldn't be modified. It should be the standard Hawking temperature. After all we need is it's thought that the Hawking temperature is just a kinematic effect. All you need is the existence of horizons. You need quantum fluctuations of fields and stuff like that. It shouldn't matter what kind of dynamical gravity theory you're considering. However, there are at least 3 reasons why maybe this is not the whole story, and why maybe the temperature could be modified. So first of all, there is an argument by Liberati and collaborators that maybe, you know, in certain theories, high curvature theories, actually the gravitons move differently than other particles, and they not necessarily move with the speed of light. They have some kind of differentials and stuff like that. Well, of course, the speed of gravitons enters the temperature formula. So maybe it's because the gravitons actually propagate differently in these theories. The other one is that maybe in these theories, like as you know, the particles propagate from horizon to infinity, you get some weird screening effect due to nonlinearities in the field or interaction with the scalar field or whatsoever. And actually, this is this reason actually might be true, because that's precisely what this Brown and York procedure actually is suggesting. So it sort of calculates like what the temperature is as you move away from the horizon, and you see that the temperature is really modifying from the standard Hawking temperature as you would expect. Finally, what is the possibility is that we have added some boundary terms, right? And typically adding boundary terms corresponds to considering a different thermodynamic ensemble. And so maybe by adding these weird boundary terms, we have actually changed the thermodynamic ensemble. Maybe no longer we have really interpretation of temperature, or you know, some weird things can happen. So anyway, so if you are interested to learn more about this, please look up our paper, which is by myself and Marek Liška, who is an amazing PhD student at Charles University. And also we have a follow-up, much longer paper, also with Robbie Henniger. So please. That's it. And if you have any questions, please ask me.
Amazing. Thank you, David. Yes. Are there any questions from the audience here? If not, I'm actually going to thank David again, because we're running a little bit late. So let's try to skip the questions. Thanks a lot for the talk, David. Thanks a lot for the last minute acceptance. Amazing. So Morgan, hopefully now everything will be working.
Yeah, fingers crossed. So my apologies for all of these delays. I had to go back and pick up my backup laptop, but I think things should be going now. Can you see?
Yes, it's working perfectly. All right,
we're good to
amazing.
Go. Okay, so thank you guys very much. I'll try to keep things moving forward. Okay, so yeah, thank you for organizing this conference series. This has been a nice way to spend my Fridays for the last month. And today I would like to talk to you about the exploration of the Unruh effect using a new technique involved with Rindler horizon mechanics. And so we're going to be analyzing some data from CERN, and so in order to do that, let's see. Now we're going. Okay, so we're going to be looking at a channeling radiation experiment from CERN. Okay, we're going to look at a power spectrum analysis of this data. This is a little bit of background material. Okay, and then we're going to start to develop these new techniques involved with Rindler horizon mechanics. And what we're going to find is that the second law of thermodynamics is itself it can be manipulated into a particle spectrum, and when applied to that data, this provides a very easy way of analyzing this thermalized data set. And then we'll start looking a little bit at some future outlooks, especially with an eye towards experiments. And so in general, what this talk is about is looking at QED in curved spacetime and seeing what it can say about radiation emission. So with that in mind, let's go ahead and turn to this Na63 experiment from CERN. This is an experiment designed to measure radiation reaction, and they looked at 178.2 GeV positrons, so high energy positrons, which are fired into samples of single crystal silicon. In particular, we'll be looking at a 3.8 millimeter thick sample. And what you end up having is, due to the regular atomic array, because it's single crystal, the lattice sites essentially function like a waveguide. And so when the positron propagates through, it feels a harmonic potential and oscillates back and forth while it's moving through the crystal. And due to the high speed of these things, you get a very, very large enhancement from your Lorentz gamma of the electric fields. And so when the photons are emitted, you have this humongous recoil. So radiation reaction is what they're looking at. And so this was one of the first experiments that had found radiation reaction in these types of systems. And so when we collect all the data, we have a power spectrum that's energy per unit time per unit frequency. And these black data points are the data sets that we're going to be analyzing. And these various colored curves here are the standard catalog of radiation reaction models that are applied to this data set. And so what we're going to use then is we're going to look at an Unruh effect type of theory applied to this data set, where the acceleration in the system comes from the recoil from the radiation reaction. And so with that in mind, let's start looking at some observables we can compute. To analyze this, we want to get a power spectrum. So if we look at, say, the QED interaction, we have our standard gauge field, as well as our semi-classical vector current for a positron, which is coupled to an Unruh-DeWitt detector. And then so basically what we're doing is we're looking at, starting off in a vacuum, we emit a photon accompanied by a transition in our detector. And so when we compute the response function from this, we kind of have the standard structure of a scalar field response function, except this additional 4 velocities contracted with the polarization indices of our photon. So a nice generalization of the response function. And we're using our standard mode decompositions for our photons, and the power spectrum is what we're going to compute now. So let's go ahead and look at that. Okay, so if we evaluate our positron on a uniformly accelerated trajectory, right, we can compute this power spectrum here, which is an intermediate state right here. But if you notice, right, this delta T that's up top here, when we plug in our hyperbolic trajectory, that gives us identically the integral formulation of a Hankel identity. Okay, so just by manipulating that, we end up with our power spectrum here, okay? And one thing that's interesting to note about it is that these Hankel functions, okay, all obey this mathematical identity, where if I flip the sign of the index, it spits out this exponential term here. And if you look, the index is this 2 delta E over A. And so when I flip the sign in that, that's 2 pi delta E over A, which is your standard Boltzmann factor that you get. And so, that's a statement of detailed balance that transitions up or down, right? And so when we sum over both of those, we get this thermal factor, which is this guy here, right? Down here at the bottom. And so what I'm using here is I'm employing a technique from Cozella and Matos and Vanzella, these guys down in Brazil, where they were able to keep the temperature of this Rindler bath arbitrary. And so this provides a technique to actually measure that Rindler temperature to confirm that it's A over 2 pi. And then for our energy gap, we have this general polynomial. And in principle, what each of these terms should be is the channeling oscillation frequency multiplied by its amplitude. And so this is a transverse velocity. There's going to be much more to say about this term right here, but this is a fiducial Rindler term, which comes from a direct interaction with the Rindler bath. And then we're going to have our recoil term. And in general, this acceleration is going to come from something like that recoil. So we'll take an average of something that looks like omega squared over 2m, which is a typical recoil acceleration. Okay, so now what we want to do then is look at that power spectrum. We want to best fit it to the data, but first we need to make sure that the system has time to thermalize. Okay, so this right here is a thermalization time for the first best fit that we do. And we see that this implies that there's about a 22 GeV cutoff, low energy cutoff. This light blue line is the amount of time that we're actually running the experiment. So this is the 3.8 millimeter thick crystal divided by the speed of light. Okay, so we have a good thermalization time here. And then when we compute best fits above that threshold, we see the chi-squared rapidly converge into this 1 standard deviation threshold here. And what that means is that the theoretical curve on average, lies inside every single data point. And so when we compare those chi-squareds to those standard catalog of radiation reaction models, we see that there's a significant improvement when we incorporate this Unruh effect. And so we have this 22 GeV thermalization threshold. So let's go now ahead and look at the power spectrum. So this is our power spectrum best fit to this radiation reaction data set. We have that 22 GeV cutoff, and then at 30 GeV, this is where this chi-squared goes to 1. And if you notice these pink and purple curves, which are above and below here, that's whenever we deform that Rindler bath temperature by just 10% away from the Fouling-Davies-Unruh temperature. So this gives you an idea of how sensitive the data set is to the temperature of the Rindler bath. And this was the proposal put forth by Cozella et al. For measuring that temperature. So it looks pretty good, actually. And really quick, I'll just go through our best fit parameters. First of all, we have an overall scale S here, which just gives us the amplitude. The acceleration scale, right? We were expecting something at about 6.2 PeV. These are very high energies, okay, or very high accelerations, but it just comes from relativistic Newton's law here. Okay, just force equals mass times acceleration. And so when you just plug in numbers, okay, you get this PeV scale accelerations. And that's exactly what we measure when we best fit for these accelerations, is we get PeV scale accelerations. And then our channeling oscillation term, which is this guy, okay, Let me put these out here. So that's this first term right here. It's this channeling oscillation term, right? This corresponds to something along the order of an electron volt in the co-moving frame, and this is typical for channeling radiation experiments, right? And so the fact that we get something consistent here is okay. But the key piece, though, is this first one, which is this term right here. This is the one that comes directly from that interaction with the Rindler bath. So this is this Rindler frequency here, which is this number, this amplitude, multiplied by the lattice constant for silicon, which is the amplitude of that oscillation, gives you 0.01, 11, and then our best fit value is 0.012. So this is the transverse velocity, the fiducial Rindler term that we measure. So this is something that we're going to be looking at again, but this is one that confirms that we're actually dealing with the Unruh effect here. And then just for completeness, we can take the average accelerations, compute a temperature from it, and then we can compute the average of those Rindler temperatures that we measure. And we see that indeed the temperature of that Rindler bath is the Fulling-Davies-Unruh temperature here, with an upper bound at the highest frequency around 2 PeV. And so this was that realization of that proposal put forth by Cosella for measuring that temperature based on a resonant interaction with the Rindler bath, which is this A1 term here, which we confirm. Okay, so that's old stuff. Now let's turn to the new stuff, okay? So what we want to do then is go back. We want to analyze this data set here, but we don't want to look at power spectrum with best fits because these things can be pretty complicated, right? What we want to do is come up with a clever way to do this, right? And that's based off of Rindler horizon thermodynamics, right? So when you think of the Unruh effect, right, you're going to have some emitter here, some positron or whatever, right? It's going to be at some distance 1/a from the horizon, and it will emit particles into this Rindler bath and hit these particle-antiparticle pairs and essentially annihilate one while one comes out of the Rindler horizon. Or you can have like a particle-antiparticle pair gets created, one gets absorbed, and the other one comes out. And so this is kind of a cartoonish way of thinking about this Unruh effect, which is the emission and absorption of these Rindler particles. And each time, and every one of these photons that comes through, right, is the photons that we measure in the lab frame, okay? And so this covariant description offers an easier way to do it because it's based entirely off the second law of thermodynamics here, okay? So let's develop this a little bit further here. So if I have the second law, dq equals kb TdS, okay? Our Rindler frequency, which is gauged by that transverse velocity, the one that we were able to measure in that power spectrum, right, is going to set the heat flux across that Rindler horizon. So the heat flux across the Rindler horizon has to come from that Rindler frequency, okay? We know that it's beta perp times the photon frequency, okay? So that sets our dq. Their temperature, we're going to be using that recoil temperature. So here it's just omega squared over 2m. There's a little bit of ambiguity in what this what the emission time is. So I have this alpha t here. So depending on what way I'm analyzing it, I could set this equal to 2 or pi, but this is a number that I'm trying to pin down here. But it's something of order unity, 1/2, 2, something like this, right? And one of the other things that's interesting about this is that you find because this Unruh temperature is in the proper frame, which is heavily boosted. But if you want to analyze a system in a lab frame, you have to see how temperature boosts. And this showed that, at least for this system, that the temperature boost is 1/gamma. And this, I typed this up, and this got an honorable mention for this Gravity Research Foundation essay competition. So this was kind of a cool result with this. Moreover, even more cool stuff is that there was a recent paper, not so recent actually now, but by Alonso Serrano and Matt Visser, which showed that even for a black body radiator, right, if you have just a general distribution of photons which obey a Bose-Einstein distribution or a Planck distribution, that there is an amount of entropy per photon that stays in there, okay? And they computed this number. And so what that means is I can map an entropy to photon number whenever we're thermalized here, okay? And so with this temperature, with that heat flux from the Rindler horizon, and then with this mapping between entropy and photon number, we can develop a spectrum, okay? Here I define alpha as this combination of this alpha S, the alpha T, and then the beta is this alpha here. And so this is going to be just some overall best fit parameter. And then it's just 1/kBT. And so this is that pure data that we'll be looking at. We're going to try to best fit this to, okay, just for this fit alpha. And I also, as a new update, we were able to come up with another way to measure thermalization time, which is completely model independent. So it's not based off power spectrum. It's not based on any theory. I just take the data and compute the thermalization time or the emission time from that data set. And so this gives you a 12 GeV cutoff. But I just want to point out something, that this is this 3.8 millimeter crystal. If you look at this, this is only basically a factor of 2 that's in between the experimental cutoff and then our thermalization time. So it's not like we're well below this thing. We're right at the very edge. And this thermalization time has been a tough cookie to crack for this Unruh effect. And so this just shows you how close we made it. Okay. So let's go ahead and apply it. All right. We do our best fit for this figure parameter alpha. We get 1.62. Okay. This alpha t can come from the acceleration. We know that these accelerations are just at PeV scale. So I just assume that the acceleration's at something on the order of 1 PeV. And this enables us to compute that beta term. Okay. And this shows us that we have agreement between the power spectrum analysis where we got 0.012, and then our best fit based off of the second law of thermodynamics here, we get 0.022 plus or minus the 0.14, where this error bar comes from that error bar, the errors from the entropy per photon. And so this light blue line here is where this alpha is set equal to 1, and then the red is where we do that best fit for this 1.62 though. So it shows you just some factor of order unity, which is this combination of this transverse velocity, emission time, and entropy per photon. And then once we have that though, right, what we can do is we notice that there's this positron mass that's sitting over here, okay? We can take this entire spectrum and flip it on its side and solve for the positron mass, and then use the data itself to actually measure the positron mass. Okay, and so what happens then is you see this convergence, right? We're multiplying this power spectrum by omega squared. This goes as 1 over omega squared, so this thing becomes flat above that thermalization cutoff here, okay? And so we get a reasonable value for our, there's a lot of scatter, so it's not supposed to be a high precision measurement, but it just shows that these Na63 experiment with recoil is just basically a broadband mass measuring thermometer. This spectrum that you see here is just 1 over kBt, and so this is a direct measurement across multiple recoils of this Unruh temperature. And so you see that, it fits quite well. Everything looks very good. And so this is kind of the current status of this of this analysis. And just to show how robust it is, so I've typed this analysis up. It's now out for review, second round of peer review now. But I just wanted to comment that these types of experiments are actually robust, and these analyses are robust in these experiments. And so there's other data sets from Na63. And so this is kind of preliminary results that I'll show you for a 50 GeV positron, so much lower energy, but for a suite of crystal thicknesses. And so just to show you what's going on here, the top row is for a 1 millimeter crystal, the middle row is for a 2 millimeter crystal, and the bottom row is for a 4 millimeter crystal. And here we have, in this case, the best fit power spectrum, but we see in this case, the 1 millimeter, we do not have time to thermalize. Our second law spectrum basically kind of looks like garbage, and our mass spectrum doesn't even converge, okay? But then now for the 2 millimeter crystal, we're kind of right on that razor's edge where are we thermal, are we not? But it looks like we're able to kind of get away with it. And so we see the convergence, and then for the 4 millimeter crystal, we're good to go, and we see the convergence wherever we need. Likewise, this is more crystals that we have, 6 millimeter samples. And again, we see that the thermalization time is upheld in both cases, and we see the convergence and very nice spectrum. What's interesting about these two is that it's the same crystal, same beam, but they change the incident beam angle. And so what that does is that gauges that transverse velocity. And so what this is a tuning of that Rindler frequency in the Rindler bath. So it's a tunable interaction with that Rindler bath that we're seeing right here. And so these experiments and these systems offer a very, very nice way to look at things. We can probe this alpha parameter that I showed, which is this Rindler coupling with emission time and entropy per photon. You can measure things like positron mass. And even if there's other processes there, some like higher order harmonics or spin flips or any other sort of thermodynamic object that can be lumped in as a chemical potential or anything that can go into this second law, you could solve for this thing and potentially probe them in these systems. And so this kind of just shows that that particle physics, namely ones with radiation reaction or anything that has large accelerations, can probe this Unruh effect, and we have a nice way of looking at it with this thermodynamic spectrum. And so then just to kind of close up things, if we talk about experiments, right, we've seen that Na63 has some nice experiments, right? Here's some of their data sets. There's also a lot of consortiums that are developing for high energy electron laser beam interactions. And so there's people that are applying for money with these. SLAC, the Facet 2 lab, is looking at these high energy electron laser experiments. And the Annabelle experiment, which is going to be a plasma mirror, so to probe things like the Fooling-Davies effect or the moving mirror effect. And then also at NIST in radiative beta decay, we're able to see things or potentially see things where there's thermality. And so I think that in particle physics, there's a lot of potential for, as already been seen, for measuring the Unruh effect and for exploring it. And so just to conclude, Unruh effect using recoil, the recoil acceleration with sufficiently thick crystals can give us a way to look at the Unruh effect. Larmor emission with thermalization describes this data. And then there's this new kind of covariant description using Rindler horizon dynamics that describes the data quite well, and it's robust across multiple data sets now. Okay. And then a prospectus about particle physics thermalizing in these experiments. I would like to just give a short advertisement to Mike Good, whose talk is in 1 week, and he'll be describing another experiment from this radiative beta decay from NIST, where we see thermalization with a 1D Planck distribution. And so thank you, everybody. Thank you, Rick, for all this this mess with the Zoom stuff. And if there's any questions, I'd be happy to ask. And thanks again.
Yeah, thank you so much, Morgan. Yeah, are there any questions from the Zoom audience here? If so, you can feel free to unmute yourself and ask.
Hope that wasn't talking too fast. That was a little jittery running around getting his computer fixed.
No worries, no worries. I do have a question though. It's
Yes, sir.
so I think that this whole idea of probing the Unruh effect indirectly by probing the radiation from the acceleration, I think is very interesting. It's a very interesting program. The thing that I wonder is, so usually you need to have an energy gap in order to really be able to get your system to thermalize, right? In the typical sense of thermalizing, right? So say in the case of the protons in CERN, what would be the corresponding energy gap that the protons would have? Because of course don't measure whether the protons are thermal in the end or not. What you measure is the acceleration radiation from that. But
yeah, the radiation.
If you
from
were to have
positrons.
access to the proton, what would be the energy gap in that case?
So typically what you have is whatever process is happening in the co-moving frame is usually going to be, so if it's the spin flip, in this case, what we have is multiple, so there's multiple examples of things, okay? Two examples are not grounded in the literature in terms of Unruh effect. One is, so the first one is this oscillation frequency omega. So as the positron is decelerating actually, right? It's oscillating transversely. Okay, and then so the idea for how this came from was looking at Cherenkov radiation. Okay, so if I look at Cherenkov radiation with an Unruh-DeWitt detector, if I have a co-moving oscillation that's there, right, it just presents itself as a frequency in the energy gap. And that's basically this is the anomalous Doppler effect. So I had anomalous Doppler effect as an example to claim that this omega is going to be there. Okay. Likewise, for recoil, the recoil correction to Cherenkov is known. You can compute it just kinematically. And that's where you get this recoil kinetic energy from. Okay. So these two things were guesses. Okay. Now, there is literature from Redis that shows that there is going to be a term like this that comes from the Unruh effect. So this one is grounded in the literature. But the important one, for at least what I was doing, this comes from this work from Matas, and there was from Kozela on how to measure the Unruh effect using essentially a co-moving cyclotron oscillation. And there was also a paper from Patenkar and Kolakar who looked at the Unruh effect with transverse drift. Okay, and for those cases, as well as in this paper, whenever I computed this one, you go in the Rindler frame and you show actually you could show that it's the transverse oscillation, that it's this term specifically that you resonantly couple with. From the Rindler bath, right? And that's the term that's necessary to develop the covariant description. So I compute some process in the Rindler frame, and then I compute some process in the lab frame that's accelerated to make them covariants. It's this term that does it, okay? And so this is the one that you get. And so in general for, how do you get a two-level system on a positron? It's not like something's clicking. It's what sort of dynamics are occurring in that co-moving frame. If it's a spin flip, it's a transverse thing, and that's the one that gives it to you. And so and the recoil one as well. That was done by Redis. I wasn't aware of that when I did this, but yeah, the recoil one has been shown that it's actually what thermalizes the transverse recoil actually is identically, and this comes from Volkov states quantizing things in laser fields. I mean, it's a very rigorous derivation of that one. But yeah, so co-moving oscillations, co-moving processes sets energy gaps for fundamental particles.
I see. Thank you so much. That's very interesting. All right, so let's thank Morgan again.
Yeah, thank you guys again. I appreciate the patience.
No worries. Yeah. Thanks a lot. Okay. And now we're going to move to the next speaker. So we had some changes in the ordering here. So our next speaker is Mojtaba Shahbazi. I think that you're here, Mojtaba? Nice. So if you want to start your camera and share your screen.
Okay. Well,
Amazing. I think that we can see your screen. Yes. But now yeah, there you go. Now we can see the presentation properly. We can see you as well. So, Mojtaba, please go ahead. The floor is yours, and tell us about how analog gravity resolves theoretical physics problems, please.
Okay, thank you. I'd like to talk about analog gravity and particularly about information paradox in theoretical physics and how analog gravity could resolve this problem. We go through to analog gravity, what is analog gravity, and how people see the analog gravity in laboratories, and then go through information paradox. And at the final, we get back to island prescription and analog gravity. Okay, what is analog gravity? If we've got a fluid, a rotational fluid, we've got this equation for a rotational fluid, the Navier equation, and continuity equation. If we change the variables, we can get to this equation and rewritten this equation in terms of a scalar field theory in a curved background spacetime. So a fluid in a flat spacetime could play the role of a scalar field theory in a curved background space. So this spacetime, this curved spacetime, could be a black hole. In this way, a fluid can mimic a black hole, but the difference is that in black holes we've got a speed of light, but here we've got a speed of sound. So these are some solutions fluid. We call it dumb holes because wave sound cannot escape these regions. Okay. In laboratories, people produce some dumb holes in this setup. There is a wave generator, there is a barrier. When the waves go through the barrier, the speed exceeds of sound wave, and then this region could be a dumb hole. So if you turn on a speaker here, the sound wave can go through the dumb hole, but they cannot escape. And this is a natural dumb hole, a drone. When we turn on a speaker here, the sound wave can escape this region. Okay. If we want to simulate an ADS-Schwarzschild black hole, we just turn the metric of ADS-Schwarzschild to this form by change of variable, and then compare the metric of ADS-Schwarzschild to analog black holes or analog space-time. And then we can read off the fluid quantities. Rho is the density of the fluid, and V is the speed of fluid. So if we want to simulate ADS black hole, ADS-Schwarzschild black hole, by a fluid, we can just prepare these quantities in our laboratories. Then the fluid mimic the ADS-Schwarzschild black hole. Okay, let me go through this part and skip this part. Okay, information paradox. We know that if we've got a field theory in a curved background, this leads to Hawking radiation. Hawking radiation is a thermal radiation. If the black hole started by the initial state of black hole would be a pure state, then at the final stage of evaporation, we know that the state of black hole is a thermal state. This is in contradiction with the unitarity of quantum mechanics. We can show this by entanglement entropy. Entanglement entropy is defined as the trace of density of matrix. We know the density. We know that entanglement entropy by unitary evolution is constant; it doesn't change. So when we start by a pure state and then goes to a thermal state, entanglement entropy wouldn't be constant. So this is the paradox. Okay, people believe that holography can solve this problem, the information paradox. But before that, let me draw your attention to the page curve and page works. A page show that I wouldn't go to any details, just goes the result. Page showed that if you've got a black hole and a medium, and the black hole evaporates, but Page actually consider quantum systems, not a real black hole. So the entanglement entropy of the system would be follow this curve. We call it Page curve, and this turning point is Page time. So if any quantum system follow unitary evolution, we expect the system, the entanglement entropy of the system, follow this this curve, Page curve. Okay, people how consider entanglement entropy in holography. This is done by the celebrated formula of Ryo and Takayanagi. Sergio talked about entanglement entropy, so I skipped these parts. This formula got some problems because they cannot compute the quantum corrections. People try to alter this formula, and finally, people propose that if we've got this formula, which is called island formula, this island formula can, retrieve the Page curve for evaporating black holes. But the point is that this island formula is really ad hoc solution to information paradox because people just add in some terms with no reasons. We'll show that analog gravity can explain why we should add these terms, but in a non-ad hoc manner. How people compute entanglement entropy via island prescription. If we got two-sided black holes, ADS black holes, because we are working in holography, in ADS spacetime, the black holes reach equilibrium and they cannot evaporate out. So we should attach some thermal bus to the boundary, and then black hole evaporate, Hawking radiation goes through the thermal bus. And if we want to compute the entanglement entropy through island prescription, before the page time, we should compute the area of these patches. And after the page time, we should compute this area, because this area is detached from the other area. We call it island. So if we want to compute this island prescription for a two-sided black hole, find that the entanglement entropy of the black hole follows the page time. So this is a resolution. But as I told you, this is an ad hoc resolution. How analog gravity provided region to island prescription. If we compute the entanglement entropy of an evaporating black hole, this is the term we get before the page time. This term is time dependent, and this is responsible for information loss, because after the page time, this term blows up and then the entanglement entropy doesn't get back. So this term is responsible for information paradox. We work on this term in analog gravity, and we showed that this term could be translated to the information loss of the fluid over the dumbhole's horizon. So if we simulate a black hole in a fluid as a dumbhole, we see that this dumbhole evaporates, and people observe Hawking radiation in laboratories. And if we want to translate this term, this time-dependent term, we'll see that this term is analogous to momentum loss over the horizon of the dumbhole. Okay. We'll see that these black holes are stationary. So if we apply on the horizon of these dumbholes, you see that the momentum going into the dumbholes would be equal to the momentum going out to the dumbholes. But the island prescription doesn't consider the going out momentum, momentum going in. So if add this momentum, we'll see that we get to this result. This is exactly what island prescription proposed. So, analog gravity showed that if we apply Newton's second law on a downhole horizon, we can get to exactly the same result of island prescription. But here, this is not ad hoc solution because we apply Newton's second law, which is really trivial for our dynamics. Thank you for listening.
Amazing. Thank you so much, Mojtaba. Actually finished super in time, according to this way earlier. So I think that there's a question from David. There's a question from Morgan. So David, you raised your hand first. So please go ahead.
Hi there. Very nice talk. So I missed that little bit. Did you say that you can actually simulate ADS black holes in this, fluid correspondence or whatever?
Yeah, we can, we can build some fluid in laboratories that mimic exactly the dynamics of ADS Schwarzschild black holes.
Okay, and is that like arranged by some kind of, reflective boundary conditions? Because one of the basic properties of ADS is that it's sort of, confining, is that everything stays inside the ADS. It's like the box. Is that what you have, or do you have to impose some boundary conditions, or what do you do?
Actually, what we are obsessed is the equations of motion, only equations of motion. We're looking for a fluid that satisfies the equations of motion ADS black holes. That's it. This is different, but, I think you are considering holography, and in holography, we consider all of things. But in analog gravity, we're just looking for equations of motion, identity of equations of motion.
Okay, thank you.
Morgan, if you want to go.
Okay, thank you. This is very interesting. I was curious about this. You had shown that there was an entropy associated with momentum. I was curious if you could just maybe tell me a little bit more about where that comes from, or how to maybe think about that, or just what is the nature of that? That was kind of an odd thing to see.
Actually, we see a real black hole. We see that the entanglement entropy is time dependent. And if we translate these black holes into a flow quantities and stuff in analog gravity, we see that horizon. Actually, we've got two different problems. The regional black holes and the analog black holes. These are different black holes. But we know that the equations of motion of both are the same. That's it.
That's interesting. Thank you.
Amazing. Are there any other questions from the audience? If not, thank you, Mojtaba, again, for your talk. It was truly very interesting. Then let's move to our next speaker. Our next speaker is Nitica. Nice. Can you just start sharing your screen and maybe say a couple of words so that we're sure that the audio is working?
Yeah, I can share my screen when it says that the other participant has to stop sharing. Can you help me with that? Ah, perfect. Okay, I hope you can see my screen.
Yes, everything is working now. So please go ahead, Nitica.
So firstly, I want to clarify my affiliation. So I was at PI long ago, but then I did my first postdoc in Gdansk, and now I'm moving from Gdansk to Naples. So this is where I'm starting my second postdoc. And I want to talk about research that started during my PhD and how it's ongoing. And there are some really nice open questions that I want to talk about. And usually we get stuck at some point of understanding the Causaloid framework. So I've tried to have a version that is something we can all follow to just understand the main broad ideas that are going into this research, let's say. So let's see. So some background on the Causaloid Framework. It's a framework introduced by Lucy and Hardy at Perimeter in an attempt to go towards quantum gravity from a perspective of taking general relativity and quantum theory as two pillars at an equal footing, and trying to marry the radical aspects of each theory together. Now, the Causaloid Framework is not a theory, it's a framework to accommodate a landscape of theories that should be compatible with dynamic causal structure and probabilisticness, and even some versions of them together, which is known as indefinite causal structures nowadays. And before we go into all the details, this is the picture I'm going to end with, and I would like to also begin with it. Which is where all of this has led to. So using the Causaloid Framework has helped classifying some theories. So there's some hierarchy known as Sorkin's hierarchy, which relates the number of real parameters you need to describe some state with respect to the number of real parameters, the number of perfectly distinguishable states you can have of that system. And this is given by a parameter R, which you can plot on a graph, which distinguishes classical probability theory and quantum theory, right? What we do is we introduced another hierarchy, which we call lambda OD sufficiency. And we will show how both of these hierarchies work within the Causaloid Framework. But the thing that we learned by studying this hierarchy is that a class of generalized probability theories called the duotensors, as well as bipartite process matrices, fall in the same rung of this hierarchy, which is kind of the upshot of this talk, because what this might help us with is kind of a program for reconstruction reconstruction for quantum gravity, akin to the reconstruction program for quantum theory from physical principles. And this is something that we are still figuring out if this hierarchy can help give us one of the physical principles towards that. Okay. So what is the Causaloid Framework in a nutshell? It's a framework where we are centering operational methodology. So what we have is that we assume something very big. We assume that we have all the logical possible data that you can have in whatever you're studying. Let's say the universe, but maybe let's start with something smaller, which might be a smaller region, your laboratory, for example. And on this data is given to a person in a room through these cards, which have some information on them. They have information of what location at which this experiment was conducted, what actions were done, and what observations were found. And now this person has all these cards, and they go through organizing these cards, and they find correlations within it, because any physical theory will correlate this data. And then the task is to compress this data such that you end up with the fewest number of cards, such that you can go back to the full set of cards if need be. And what we are really interested in are conditional probabilities of what happened, what outcome you found in some region, given what actions were done in that region, and actions and observations in any other region. So these are the things we want to be able to calculate, these probabilities. And at the level of operational methodology, we say this is akin to the theory itself at the level of, without going into ontology, let's say. And of course, we need to be able to go to these probabilities from some notion of state and measurement. But one of the motivations for the Causaloid Framework is to not have an assumption on the order of causal structure, and yet the notion of state and measurement itself have a notion of causal structure embedded in it, where we think of the state being prepared and the measurement that happens after a state is prepared. So here we try to generalize these notions. So here you have some probability. This is a number, and it's indexed by all these wires corresponding to the different regions. and the alphas correspond to the index on these wires. And we want to understand this probability in terms of some generalized bond rule, where the generalized measurement is essentially anything you can do in this region that you're considering, and the state is everything that's prepared and you don't have control over within this region. So these equations can look differently depending on which wires are on your measurement and state, for example. And then, of course, this is now just organizing the cards that one started with, and we want to compress them. And there are 3 levels of compression in the Causaloid framework. So let's talk about the first 2. So the first one has to do with tomography. That's why we call it tomographic compression. And essentially what you do is you take each region and you so the lambda box represents a matrix, a very rectangular matrix at that, which takes you from some index alpha to a fiducial set indexed by L1 for the region 1, and so on for each region. And what you might want to think of is maybe an example will help. You can think of a Stern-Gerlach experiment, and you can say that, well, alphas correspond to all the settings, and all the settings are all the angles, and therefore the list of alpha is quite big. But we know that to do tomography, we don't have to know the outcomes for each theta. We can go to a fiducial set, and this is what this set looks like here. But now, once you do tomographic compression on each region, each elementary region, there's some more compression that can happen, which comes from causality. So when you compose these regions together, there might be some causal relations between them that reduce the description that you need to describe the total state compared to the, let's say, the individual states. And this we see maybe from an example of like composing quantum channels. So if you compose 2 CPTP maps, the resulting CPTP map will be described with lesser elements. On the other hand, if you have 2 channels just composed parallelly, then the number of parameters to describe this composed CPTP map is also equal to just the multiplication of the original 2, which means that compositional compression is non-trivial when you have some causal adjacency between these regions. And then one can write down the causaloid itself by writing down the tomographic compression lambda matrices and the compositional compression lambda matrices for all regions. And this itself is able to give you back all the conditional probabilities for all alphas. So we call this the causaloid, which is akin to the theory, describing the theory itself at the operational level. And you can use this causaloid to define a causally neutral product. So the causaloid product, which you can reduce to the tensor product or composition in quantum theory, but more in GPTs, this would just be parallel composition, sequential composition, and so on. And if you have indefinite causal structure, it might be something in between. So let's go to the third level of compression, which we didn't touch on, which is called meta-compression, because what we do is we compress the causaloid itself. So the causaloid was this tomographically compression matrices, these lambda matrices, the compositional compression matrices, which I've listed out in terms of like the number of wires that are going in and out. So 2 region, 3 region, and so on. And as long as you can compress the description of the causaloid itself, given some rules, you have some meta-compression. And here we define a hierarchy by cutting this off at D regions. And as long as you provide the rules to get back lambda ON, where n is greater than D, then you can say you have some meta-compression with your causaloid being described by a smaller list. And we call this rung of the hierarchy lambda OD. And of course, lambda O1 is, so if we only had everything explained through tomographic compression, it's not a very interesting level because we don't have any causal connections between regions. So this is something that is kind of trivial. So the next, the non-trivial layer would be lambda O2. So we go to lambda O2 and try to study this. So for the purposes of this talk, this is sufficient to consider 3 regions only. So here we had N and D. So if you set N to 3 and D to 2, this is what we're trying to show here explicitly. And here then we can just list the causaloid explicitly in terms of tomographic compression, compositional compression of 2 regions, and compositional compression of 3 regions. And you can define diagrammatically like the equation that must be satisfied if you want to describe this matrix in terms of these other 6 ones. And you can also, let's assume some causal structure between these regions. You don't have to do this, but this will come handy. So we're doing this here, where we say that region 1 and 2 are causally adjacent and region 2 and 3 are causally adjacent, but 1 and 3 are not. Then the above equation reduces from the previous slide, reduces to this equation, where we can characterize the lambda matrices. And we can also, the indices belong to these omega sets, and we can also describe how these sets are related. And now we're going to use this equation again and again. So we are going to okay, before we go into this, just to say that we assume some specific causal adjacency relations between these 3, but you can do it more generally. It's completely allowed. But we did this particular case for some utility that you'll see now. So now we try to apply the Causaloid framework on the duotensors and the bipartite process matrices one by one, just to show the conclusion that I started with, that we find it on a particular rung of the hierarchy. So let's start with this equation, the Causaloid equation, and we try to massage the duotensor, which is a framework for GPTs that have a circuit structure. So they're a family of theories, and you can massage this such that you can now start trying to identify these lambda matrices in terms of the objects of this circuit diagram. And once you do this, you might realize, if you stare at it for long enough, that the lambda matrices can be understood in terms of these duotensor objects, which is beyond the purview of this talk, but I'm happy to talk more about it. But what we do is we show that you can actually describe any lambda O3 matrix in terms of the tomographic compression and compositional compression of 2 regions. And therefore, we can conclude that the duotensors fall on the second rung of the hierarchy we introduced. But the duotensors are a kind of post-quantum theory, but they don't have indefinite causality. So the next question was, we know some frameworks such as the bipartite process matrices, which have post-quantumness, and how they would look like within this framework. And now, again, it's the same equation we started with regions 1 and 2 causally adjacent and regions 2 and 3 causally adjacent. And we want to check if these equations hold for the bipartite process matrices, where we identify the bipartite process matrix as region 2 and the 2 CPTP maps A and B with region 1 and 3. And you can do at the level of sets, you can check that this equation holds. And then once you do this, you can write down the elements of your process matrix calculations and check if this relation holds. And since it does, we can conclude that the bipartite process matrix is something that these things that violate causal inequalities, have indefinite causality, also fall on the second rung of the hierarchy. So we have two different very post-quantum directions that fall in the same rung of this picture, which is in terms of this hierarchy that we talked about. And going forward, I would like to figure out what this means, if it can help us shed some light on constraining this landscape for quantum gravity. And one way to do this, one open question that's on my mind, is to see if an operational version of GR could be seen within the Causaloid framework through these through this lens, and where it would fall on this table to shed more light going forward. Yeah. So I would like to stop there with this slide depicted. Yeah. And thanks for having me in this session, Rick.
Amazing. Thank you so much for joining, Nitica. About the affiliation, let me just tell you because you're a member of the ISRQI, I don't have any control over the affiliation there. It's associated with your ISRQI account. So you have to change it in your account there if you want to see it changed. Yes.
Okay. Okay, yeah. Thank you so much. Yeah.
No worries, no worries. I'm gonna send you a short message about how to actually change it, but that's yeah. Thank you so much for your talk. Are there any questions about the talk? So if there are no questions, okay, Alessio is getting set up there. But if there are no questions, I don't have any question about the content. But do you think that after ChatGPT was released, you're gonna have to rename the generalized probability theories so that people don't get confused by the generative pre-trained transformers?
This thought has crossed my mind, of course, but I think now like GPTs also have like ambiguous definition within physics as well. So probably the best way is to not use the acronym all the time and always go like with the explanation first. But yeah, it's also like I also have this term called meta compression. This was before Facebook renamed themselves to Meta, and yeah.
That's fair enough. Thank you so much, Nitica. And all right, thank you so much for being a part of it. So, Alessio, if you want to unmute yourselves so that we can try to hear you and also start your screen.
Okay, can you hear me?
Yes, we can hear you.
Share my screen. Could you see him?
Yes, that's amazing. All right, so next speaker is Alessio Lapponi, who'll talk about relativistic quantum communication between harmonic oscillator detectors. Alessio, please, the floor is yours.
Thank you, Rick, and good morning, everybody. Yeah, as I said, I'm Alessio Lapponi, third year PhD student in the Scuola Superiore Meridionale in Naples. I have to update my RQI account as well because of the affiliation, but it's okay. Okay, basically, I want to talk about the communication between harmonic oscillator detectors, and this talk is mainly based on a paper I published in June of this year with Dimitris Moustos, Professor Bruschi, and Professor Mancini from the University of Camerino. But besides that, I'd like to share with you even further results I've obtained. So, summarizing, I'm considering two static detectors in a 3+1 dimensional Minkowski background. And basically, the protocol is Alice that wants to share its state to Bob via a massless scalar field. I'd like to show you how the communication between these two harmonic oscillators can be recognized as a bosonic Gaussian channel, in particular as a one-mode bosonic Gaussian channel. And secondly, I'd like to show you that the properties of this channel can be studied even beyond perturbation theory, without considering any particular situation, such as delta-like interactions between the detector and the field, or gapless detectors. So let's, without further ado, let's describe the model. Okay, I'm not talking about particle detector models because I think that people from the University of Waterloo and Nottingham have already done that enough. However, just to resume, particle detector model will consist on a non-relativistic quantum system coupling with a field observable in general. In our case, I'm considering two particle detectors, and the quantum system representing them is a one-dimensional harmonic oscillator, or an analogous system, whose Hamiltonian is given by this. The scalar field is massless, as I said, and in that case, the interaction Hamiltonian will consist on a coupling constant, a switching in function, and then a tensorial product, let's say, between an observable proper of the detector and unobservable of the field. As a switching in, I'm considering a sharp switching in. So basically, I'm considering that both the detectors interacts with the field at a time t equal to 0, and then the interaction remains constant afterwards. As the observable of the detector, I'm considering an analog of the position operator, let's say, of the one-dimensional oscillator. As a field observable, I'm considering the field operator, but with a Gaussian smearing. In this way, it's like considering the two detectors to have a Gaussian profile in space. Since we are talking about two static detectors, we don't expect any change on this shape since the two detectors are static. Okay, how will they communicate? Well, it's simple. Alice prepares state its detector in a certain state, then coupling with the field, Alice shares some information with the field, then the field propagates to Bob's detector, and Bob interacting with the field will receive part at least of Alice's message. Since we are dealing with two harmonic oscillators, the whole system could be considered as a two-mode Gaussian state. All the entropic quantities of Gaussian states could be defined through the covariance matrix of the state. In case of a two-mode Gaussian state, we have the following expression, where sigma A represents the state of Alice's detector, sigma BB the one of Bob's detector, while the off-diagonal block matrices represent the correlations between Alice and Bob's detector. The quantum channel is then the one mapping the input to the output. As input, I'm considering the state of Alice's detector at the time t equal to 0, so before the interaction with the field, while as an output, I'm considering the state of Bob's detector after a time t, after the interaction with the field has started, basically. Now, the trick to find non-perturbative solution is basically to recognize the complete Hamiltonian of the system, which is this one, as the same of the one of two oscillators in a buffer of particles undergoing a quantum Brownian motion. In that case, the field plays the role basically of a ohmic environment. In that case, the Heisenberg evolution of the moment operator of the detector is given by the quantum Langevin equation. In particular, we have a coupled quantum Langevin equation. Let's say the evolution of the moment operator of Alice is influenced by the one of Bob through this element here, which is the dissipation kernel, which is a 2 times 2 matrix in that case. And in particular, the off-diagonal elements of this dissipation kernel is proportional to the commutator between the field operator in Alice's position and the field operator in Bob's position. And obviously, we know that this commutator gives the causality of the problem. So if this commutator is 0, there is no causality, and so there is no influence between Alice's moment operator and Bob's moment operator. Now, the aim is to compute this coupled quantum Langevin equation, and we can do that. An easy way to do that, and at least to compute the communication properties of the channel, is via the green function matrix. In particular, by defining this green function, which will be the solution of the homogeneous quantum Langevin equation, we got this this expression for the moment operator, and this is very important because it allows to write Bob's moment operator and its time derivative in terms of Alice's moment operator at the time 0. But this means basically to express the output covariance matrix in terms of the input covariance matrix, and that's exactly what we want to build a quantum channel. The expression linking the output and the input will be this one, and they are dependent basically on two matrices, the T matrix and the N matrix. In that case, the quantum channel is a one-mode Gaussian channel whose properties are widely known from the literature. In particular, all the properties and even the capacities are defined by two elements. The determinant of the T matrix, this one, which is the transmissivity of the channel. What is the transmissivity? Well, basically, it's we can think on the transmissivity on the portion of input signal effectively arriving to the observer, to Bob. So, sort of a transmission coefficient. Then we have the determinant of the N matrix, which gives the additive noise. In particular, this expression here, which is proportional to the determinant of the N matrix, gives the number of noisy particles effectively achieved to Bob. So to have a good quantum channel, obviously, we should have a high transmissivity and low noise. And the capacities are entirely defined by these two elements, and now we will see that. What is capacity of a channel? Well, basically, the definition of a capacity is the maximum rate of information, which could be or classical or quantum, that the channel is able to transmit reliably. The capacity of a channel is basically both classical and quantum capacity gives the capabilities of the communication of classical and quantum information. To make you understand better this concept, if the capacity of a channel is 0, then this means that it's impossible to transmit reliably information with the channel. If instead the capacity is different than 0, information could always be transmitted with arbitrarily low amount of error. However, how would we differentiate a low capacity with a great capacity? Well, if a channel has a low capacity, then it requires more time to transmit reliable communication. I quote time because as time I intend the number of times in which we have to use the channel to transmit the signal reliably. So obviously it's always better to have a high capacity in order to have a faster communication. Now, in our particular protocol, since we are considering two static detectors in a Minkowski background, in a Minkowski vacuum, we have that it's impossible to transmit quantum information, otherwise the no-cloning theorem is violated. However, the classical capacity of the channel is always different than 0. So without further ado, now we are going to calculate the classical capacity for this protocol. And we'll see some interesting things. To calculate it, we have to find the elements of the green function matrix I described before. And it is possible to find exact solutions for them in two particular cases. The underdamped case, so when the coupling is much smaller than this number, and this is analog to the perturbation theory with a low coupling perturbation, let's say. And even in the overdamped case, so it is possible to compute exactly the properties of the quantum channel, so the these green function matrices elements, even when the coupling is much larger than this number. So even when the coupling is arbitrarily large. And the overdamped case basically means that we are able to compute the quantum channel properties beyond perturbation theory. The only non-analytical results arises when we are going to consider the resonant case, so when the coupling is comparable to this number. Now we will see case to case what happens. Starting from the underdamped and overdamped case, we have the following plots. In the underdamped case, we get a transition period, which is in general proportional to 1 over the coupling. After this, we got the capacity to reach a peak in time, and then drops to 0 afterwards. In the overdamped case, instead, we have almost the opposite situation, namely that the capacity turns on smoothly, reaching an asymptotic value for high times, in late times. And this asymptotic value is given by this. Now, from the plot, we can observe some interesting things. Let's look, for example, to the underdamped plot. In that case, the more is the coupling, the more is the capacity, and that's expected because obviously low couplings means no communication between means low communication between Alice detector and the field, and so obviously even from the field to Bob. However, in the underdamped case, we have the opposite situation, namely, contrary to what is expected, the more is the coupling, the lower is the capacity. Why this? That's that could not be expected at first. But we have to take into account even the noise, because the more is the coupling, the more is also the noise that Bob achieves in the communication with the field. In that case, in the overdamped case, the increasing of the noise, how can I say, overcomes the increasing of the transmissivity, making the communication worse. So now, what is the best coupling? If it's not an arbitrarily high coupling, the best coupling we can choose for the communication, is there a finite value for it? The answer is yes, and we can find it in the resonant case. So in a range of values for decoupling in which it's not possible to find exact solutions. In that case, we have plots similar to that for the capacities, and the best situation is recognized in the dotted line, so where the capacity remains flat, let's say, after reaching a peak. This best case scenario is reached when the coupling is equal to this expression. Here, D is the distance between the detectors, omega is the energy gap of the detectors, and sigma is the effective size. Is there also an optimizing energy gap, so an optimizing frequency for the detectors to maximize the classical capacity? The answer is yes. In this 3D plot, indeed, by numerical calculation, I have found several the values for the optimizing frequency, so for the optimizing energy gap for different detector setups, so for different distance between the detector and for different size of them. So basically the conclusion is that fixing some values of the distance and effective size of the detectors, it is possible to find values for the energy gap and the coupling that optimizes the communication. So let me conclude by discussing something and make you open questions, let's say. Basically, the first thing is that it is possible to study the capacity of the communication between two harmonic oscillator detectors even beyond perturbation theory. Because, as I said, in the overdamped case, we can choose a coupling arbitrarily high, and we got exact solutions for the capacity. However, despite it, a huge value of the coupling is not the one we want. Is not the one which optimizes the classical capacity. Unfortunately or luckily, to optimize the capacity, we need a finite value for the coupling. And I found this value as long as the optimizing frequency for the detector, so optimal coupling and energy gap for a plethora of detector setups. So I want to ask you, do we really need to go beyond perturbation theory? In the sense, this proves that we do not always need a huge detector field couplings to optimize the communication. So maybe even okay, maybe not a very low coupling, but neither a really high coupling is needed to reach the optimal communication between detectors because of the presence of the noise. The other question I want to raise is, could we find a better communication protocol? For now, the answer is yes. I found some ways to optimize it. For example, I found that the classical capacity increases if Bob's detector and the field interacts later than Alice and the field. If we delay the interaction between Bob's detector and the field, we got less noise in general, and so a better capacity. And really curious thing is that it seems that the transmissivity is proportional to the imaginary part of the Whiteman function of the field considered, while the additive noise is proportional to the real part of this Whiteman function. This could be a hint, for example, if one wants to find optimal capabilities even for other contexts. For example, I don't know, we can consider different dimensions of the spacetime, different smearing, different background spacetimes, and so on. And using this hint, let's say maybe we can, I don't know, find some better protocols in different situations than the static case. Moreover, if we consider a non-isotropic background spacetime, then the no-cloning it is possible to communicate quantum messages without violating the no-cloning theorem. And in that case, we could have even a quantum capacity different than 0. And I'm actually working on that by considering accelerating detectors with the help of Professor Lope in the University of Nottingham. Then finally invite you for further details to check the reference paper. And finally, thank you for your attention.
Thank you so much, Alessio. So, great. Maybe we have time for one question from. So, does anyone from the Zoom audience have any questions? Okay, if not, I have a bunch of things that we should definitely discuss afterwards, to be honest, because I think that I can definitely provide you with some insight on the imaginary and real parts and things like this, I guess. But for now, I'd just like to ask you whether in your protocol, whether you can, whether you would be able to get the detectors entangled using this, and whether you have quantified this.
That's a good question. Let me take the. Well, basically, I don't know, but I expect obviously that there is no entanglement in the static case. In practice, we could calculate this off-diagonal elements for whatever initial state. I don't think that some entanglement arises in vacuum. If in vacuum, in the sense, if Alice and Bob starts with their detector in the ground state of the oscillator, I don't think it arises some environment. Otherwise, we would have entanglement harvesting in vacuum. However, we can calculate the correlations between the detectors there. I expected, however, to have both classical correlation that quantum correlation. However, if classical correlation are much higher than quantum ones, we don't have any entanglement. However, yeah, it is possible with this method, basically, by calculating these off-diagonal elements.
Because yeah, we just expect that if the two detectors are exchanging information with the field constantly, then at some point they would get to a stage where they have exchanged enough quantum information so that perhaps they would be entangled. But yeah, no, let me know if you take a look at
classical information. So I expect that at a certain point there is a strong classical correlation between them, but I don't think there is entanglement.
Right, definitely. Okay, great. So thank you so much, Alessio. Thank you again. And now we go to our next speaker, who is also Alessio, but not Alessio Lapponi, Alessio Belfiglio.
Can you hear me?
Yes, perfectly.
Great.
Let me just go.
Okay.
There we go. Now you should be able to share your screen.
Yeah, now I try. Okay, can you see my screen?
Yes, but you still are not in full screen. So
okay, now I go full screen. Yeah. Now you should see the whole screen.
Perfect. Amazing. So our next speaker is Alessio Belfiglio, and he'll talk about entanglement area law violation from field curvature coupling. Alessio, please, the floor is yours.
Yes, thank you. Yes, I will come back to the topic of area law that was previously discussed, but mainly from a quantum field theory perspective, essentially, and precisely from a discrete quantum field theory perspective. So let's start with a brief introduction of the notion of area law and why and where it is important. So, okay, if we consider quantum systems, especially in quantum many-body physics, in many contexts, the degrees of freedom of the theory can be, let's say, arranged in quantum lattices. So we can consider a quantum lattice system. And an interesting question is to ask, what is the entanglement and how is entanglement distributed in a given region of this quantum lattice? And it was shown that if we consider a given region, that here I call the L, and so we trace out the other region of the system, that here is O, the entropy of this region, even at 0 temperature, is not 0. So essentially, there is entanglement among the local degrees of freedom of the theory. And the interesting question is how this entanglement scale with the size, with the boundary area, with the volume of this region. So it was previously discussed that intuitively the entropy should scale, let's say, like the volume, because it is an extensive property. But this is not always true. And in principle, this is true only in case of thermal states. If we go to ground states, typical ground states of this quantum many-body theory, the entropy scale like the area, so the boundary of the region under analysis. So we can also, let's say, set a definition for this concept. So in principle, a lattice system, in this case a system that I call psi, satisfies an area law if its entropy, so the entropy of a given whatever the region is, satisfies this expression. So it's smaller than a constant times the area of the region, the boundary of the region. And this, in principle, in case of, let's say, low energy states, so mainly for ground states of this quantum systems. But why is it important in the other quantum many-body physics, since we are interested in application of quantum field theory to gravity and cosmology? So other than, let's say, the possibility to, let's say, indicate a topological order in a given theory and to describe quantum correlation in this quantum many-body system, it can also be useful in the attempt of simulate quantum systems. So let's say, if we are able to understand how much entanglement is in a theory, it allows us to understand if we can simulate numerically the theory in some way, or we are not able to do it in case there is too much entanglement. And finally, as so connecting to the previous talk, there are possible connections with the Bekenstein formula for the entropy of the black hole and the holographic printing. So in case the entropy of the black hole, let's say, is proportional to its area, so the area of the horizon. And let's say the entanglement entropy is a leading candidate to understand what is the origin of this black hole entropy. And how can we do this? In principle, we can try to, let's say, model the degrees of freedom of the black hole by means of a scalar field. So in principle, we trace back that degrees of freedom to the degrees of freedom of a scalar field that in principle should propagate in curved space-time. But first attempts in this direction were done by considering a scalar field in Minkowski space-time. So how can we, let's say, discretize this, let's say, model theory? The first approach was done almost 30 years ago by Srednicki. And in principle, we can imagine to discretize the theory by introducing, let's say, a lattice of spherical shells. So in principle, we introduce a spherical volume. We introduce a radial distance between consecutive shells that I called A. So in this sense, we have an ultraviolet cutoff that is 1 over A. And of course, we fix the total volume of the cell by introducing a given number of shells, and so an infrared cutoff. The angular part, exploiting spherical symmetry, of course, can be expanded in terms of spherical harmonics. And so here you see the full Hamiltonian describing a scalar field that propagating in Minkowski space-time by means of this discretization procedure of spherical shells. And how to compute entanglement in this case? Essentially, that system can be traced back to the Hamiltonian of a system of coupled harmonic oscillators. And in that case, we are able to compute the entanglement entropy of the ground state because we are able to derive the density operator corresponding to the ground state and to compute the reduced density operator that is obtained by tracing, let's say, tracing over a given region of this spherical, let's say, spherical system that we consider. So this was done first. This approach was first done by Srednicki in 1993. And okay, the entropy, the entanglement entropy in this case is this formula that you see here, where the small n is essentially the number of degrees of freedom we are tracing over. And the capital N is the total number of degrees of freedom that put on this sphere. And okay, these eigenvalues can be derived from this by taking the coupling matrix, the square root of the coupling matrix. So there is a standard procedure in order to get this psi here and to derive the lambda that are derived from the coupling matrix. So in general, we want to know how entanglement scales in case of this scalar field with respect to the radius of the sphere that we are tracing over. Let's say there is 1/2 because, of course, we want to avoid to put exactly the sphere we are tracing over on one of the shells. So that's why you see there is n plus 1/2 there. And okay, this was done first by Srednicki, but then the topic was also reconsidered in recent years. In principle, you see the entanglement scales linearly with respect to the radius squared, so with respect to the area of the region that we are considering, the region we are tracing over. And another important consideration is that the total entropy is a decreasing function of the scalar field mass, in the sense that, let's say, is harder to entangle degrees of freedom in case the mass of the field is higher. Of course, this is quite intuitive. And in principle, one can also apply a perturbation theory, so a perturbative approach, in order to compute the entropy in case the mass of the field is sufficiently high. So here you can see that taking a larger mass, you see the perturbative approach gets closer and closer to the numerical result, where numerical is the standard procedure that I discussed before, in the sense to derive exactly the ground state of the Hamiltonian, and from there computing the eigenvalues that give the entanglement entropy. So, okay, this approach was done in Minkowski spacetime. Of course, if we want to connect the entropy of a scalar field, that, moreover, this approach was also reconsidered some time ago in order to show that the degrees of freedom of this scalar field can mimic the, let's say, metric perturbations in a black hole spacetime, and in particular tensor perturbations. So that's why we still consider scalar degrees of freedom, so a scalar field, in order to compute entanglement entropy and to try to get to know something more about the area law behavior. So, but that approach was done in Minkowski spacetime. Of course, we are interested in curved spacetime in some sense, because we want to link to the entropy of black holes. And this approach was first tried in this paper that you see here, in which it was shown that if we consider a static and spherically symmetric spacetime, so a spacetime of this form where f of r equal, say, h, let's say, are the horizon, so it depends. In the following, we will see the sitter spacetime. So we have cosmological horizons and we have black hole horizons, but in general, okay, this is the expression we will consider with just one lapse function, just one f of r. And it was shown that if we move to Lemaitre coordinates, so if we do this change of coordinates, and we fix the Lemaitre time, here I fixed equal to 0, but okay, in general, if we fix that time, we can apply to the Lagrangian and then getting the Hamiltonian a canonical transformation in order to obtain an Hamiltonian which had the same form of the one that we discussed before. So the same behavior, the same terms, in case we can apply this canonical transformation, and in case we can, let's say, fix time. So this is still a static point of view. At the end, I will discuss also some possible generalization to let's say, Friedman-Robertson-Walker spacetime. So in case of dynamical spacetime with a given scale factor. But okay, at the moment we are able to solve these models. So with this kind of Hamiltonian. And as I said, this has the same form of the previous Hamiltonian I discussed. And so in principle, we are able also in this case to compute the entanglement entropy. And this is an example in the work I introduced at the beginning, in which we fix some parameters. Of course, one has to consider that we have to put, let's say, a cutoff to the total number of, let's say, AL, in this case, so the spherical harmonics expansion, in order to compute numerically the entropy. And here we set 1000 because after, let's say, the relative error when we reach AL equal to from 800 to 1000 is very, very small, and that's why we can cut off the theory there. We should also say that this approach has the problem that we put a cutoff by hand in this case, and we also have to fix the total number of shells we consider. So let's say in some sense the radial cutoff is put by hand, setting the total number of shells we consider, while the angular cutoff is put by considering the relative error that is obtained up to a given value of L. So this is maybe one drawback of this approach, but this is at the moment the best and let's say also the simplest approach to derive the entanglement entropy. So this is the first generalization to the case of a curved space-time. So even if it's static and spherically symmetric, but an interesting question that we pose is, what if we had some interaction to the theory? So what happens if the field is not free and, for example, is coupled to the curvature? This is important mainly, for example, in case of, let's say, cosmological inflation, the possible couplings between the inflaton field, so let's say, in this case, a scalar field, and space-time curvature can be very important because, for example, some models are ruled out, but in case of power law potentials. But if we introduce a coupling with the curvature, this model can be feasible. So non-minimal coupling is an important topic in cosmology, and represents also the simplest possible interaction that we can add to a free model. So what happens in this case? We discuss this. We study this topic in our work. So the point is, it's to add the field curvature coupling term. So we have an additional term to the previous Hamiltonian, and of course we have to discretize the scalar curvature. But since we work with these spherical shells in a static spherically symmetric spacetime, we know that I put here the well-known expression for the rich scalar curvature, and of course one can discretize this curvature in order to get a discrete term in the Hamiltonian and to compute the new entanglement entropy in case of a non-minimally coupled model. So by this approach, we have this term, and in principle, we can study this additional coupling in, let's say, whatever static spherically symmetric space-time. So the point is the following: if we consider a de Sitter-like space-time, so if we consider a space-time in which the scalar curvature is constant, here the plot is for the Schwarzschild de Sitter, which of course is one of these cases. The field curvature coupling add a constant term to the total entropy, because of course it's like if we have an additional mass-like term in the Hamiltonian. So in principle, we cannot modify the behavior, so we cannot violate the area law, so the dependence of the entanglement entropy with respect to the radius or to the boundary area. We can only modify the total amount of entanglement, because as we have discussed before, in case we have a large mass, we have less entanglement. So of course, in this case, if we have a positive coupling constant, so we have a positive term, we have less entanglement because it's like the mass of the field is higher, and the opposite in case of negative coupling. But of course, this is a special case, because in case of space-time in which the curvature is not constant, so here we were starting to discuss regular black hole space-time. So this is the Hayward space-time that is one proposed by Hayward in 2006. We can have violation of the area law, because we have a coordinate-dependent curvature term. So in principle, area law can be violated because of the presence of a term that depends on the coordinates, and so is no longer constant as before, and that's why this can violate the behavior of the area and can lead to violation that, of course, are possible for let's say whatever space-time that contains a curvature-dependent term, if the coupling constant is sufficiently high. As you can see, increasing the coupling constant, we get higher modification. Just to conclude, I want to summarize. So in this work, we show that in principle, the presence of an interaction between the field and the scalar curvature can lead to violation of the area law. So the dependence of the entanglement entropy of the field with respect to let's say, the area of the region that is traced over. But there is also still a lot of work to do. In principle, we are working on two main topics at the moment. One, we want to generalize this approach to the case of the entropy of the horizon. So for the moment, we work close, let's say, to the origin, close to r equal to 0, because we have to take a small step in order to, and we are limited by the fact that by the numerical calculations cannot get, for example, a capital N equal to, let's say, 1 million. We have to be close to the origin. But we want to generalize this approach to the case of the horizons, and in that case, one usually consider the near horizon approximation, and one can consider different choices of the coordinates in order to get the entanglement close to the horizon. And as a final topic, we are also, let's say, trying to apply this approach, so to study the entanglement entropy and energy in order to understand the stability of possible black hole spacetimes and also the properties of the horizon in this corresponding spacetime. And with that, I want to conclude. So thank you.
Thank you, Alessio. That's a very nice talk. So are there any questions from the Zoom audience? Well, if not, I do have a question. So you use this lattice approximation, right, for modeling your quantum field. And as far as I understand, this lattice approximation only converges or makes sense to really take the lattice limit when you have a mass, right? Because if you don't have the mass, then I'm not really sure how to handle the interplay between the lattice theory and the quantum field theory and the massless limit. So the question is basically whether you can say something about the massless case using this approach, or whether you really rely on the mass.
Well, in principle, yes, we rely on the mass, but let's say from a mathematical point of view, as we can see from this Hamiltonian, in principle, also in the limit of negligible mass, that it was also studied. For example, I showed, in principle, with this approach, we can also, maybe we cannot figure out how, let's say, the degrees of freedom, what they represent in that case. But in principle, with this approach, we can see from this Hamiltonian that even in case of zero mass, we still have this term, so we still have entanglement generation, and we still have an area law behavior. So yes, I agree that in principle, yes, it's not intuitive in that case how to let's say how we can consider degrees of freedom, mass as degrees of freedom in the lattice model. But in principle, also in case of mass equal to 0, in the limit of m equal to 0, we still have area law behavior in case of minimally coupled theories. So yes, we can see from here. So,
amazing. All right. So Alessio, let's thank you again.
Thank you.
And yes, so our next speaker is Sascha Lang. Let's get everything set. Sascha, if you can just
see me, hear me.
Yes, we can hear you. We can see your screen. We can see you, but your screen is not in full screen yet. Now it is. So perfect.
Do you see the mouse?
Yes, we can see the mouse.
Great.
So Sascha, please go.
Wait, I don't want to start with the supplemental material.
That's actually a good idea. So yeah, our next speaker is Sascha Lang, and he'll talk about spontaneous Ginzburg excitations of a superluminal Unruh-DeWitt detector in a dispersive and dissipative medium. So please, Sascha, the floor is
Yeah, so thanks a lot for organizing this event and giving me the opportunity to present this work, which was done together with my PhD advisor, Ralf Schützold, in collaboration with Bill Unruh and with our experimental colleague, Roland Sauerbrei. And I want to start with a brief recap on some known results regarding the excitation probabilities of moving Unruh-DeWitt detectors, which are initially in their quantum mechanical ground state. And when talking about Unruh-DeWitt detectors today, I always have a point-like two-level system in mind, which moves along some prescribed classical trajectory. And later on, we will consider a scenario where such an Unruh-DeWitt detector is realized by means of a hydrogen atom. And there are quite famous results for particle detectors moving through a relativistic 1+1 dimensional scalar field in its quantum mechanical ground state. It is known that particle detectors in inertial motion do not have a chance to get excited, so they won't click. The situation is different for accelerated detectors, for example, for detectors on uniformly accelerated paths. They have a chance to click. And regarding inertial motion, there is one hypothetical exceptional case to be mentioned. In principle, if one was able to realize a superluminal particle detector, this would have a finite chance to get spontaneously excited. And this leads to the question, what happens to superluminal detectors which move in dielectric media, in which there's a reduced effective speed of light as compared to the speed of light associated with the ordinary light cone in vacuum? In such scenarios, it should be possible, at least in principle, to realize particle detectors which move at velocities which are greater than the medium speed of light, but below the vacuum velocity. Those particle detectors turn out to have a small chance to get spontaneously excited. And the question is, why is that? Well, let's consider the situation from the perspective of such a moving detector. If you have such a moving detector, this detector perceives the surrounding field modes to be Lorentz boosted in energy, and it perceives this boosted energy here. And if the velocity of the detector exceeds the phase velocity in the medium, then those energies associated with surrounding photons are negative. And then creating a photon in such a negative energy mode sets free an energy, and this energy can be used to excite the atom. The mechanism is sometimes called the Ginzburg effect, and by Ginzburg himself, it was called the anomalous Doppler effect. So it's actually related to what was mentioned before that today. This Ginzburg effect has been studied before, but we will consider the situation of a superluminal atom or particle detector moving in a dispersive medium. And as a dispersive medium, we will consider a toy model, which is called the Hopfield model. And in its simplest version, it yields a dispersion relation of the form given here. We have two discrete energy bands, omega minus and omega plus, and they are separated by a band gap just above the resonance frequency omega of the medium. For small energies, the lower energy band is approximately linear. At larger wave numbers, this flattens out. And each wave number for a photon in such a Hopfield dielectric has its own characteristic medium speed of light, so its own characteristic light cone. And assuming an inertial detector which moves at a fixed velocity, this picture suggests that it should always be possible to find a field mode which has an even slower propagation speed. And this can be accomplished by going even closer to the medium resonance, because for very large wave numbers, where this lower band grows close to resonance, the phase velocity drops to zero. So this could suggest that arbitrarily slow detectors always have some chance to get spontaneously excited, and we want to investigate whether that's indeed the case. And as already mentioned, such excitation processes would involve those slow field modes close to resonance. And in realistic media, one has to include dispersion and dissipation, so material properties in this parameter regime. And that's why I first want to briefly introduce a model for a dispersive and dissipative medium I worked on previously. We will envision a medium which is 1 + 1 dimensional and lives on the x-axis of some coordinate frame. And we assume, just for simplicity, the electric and magnetic fields inside this medium to be fixed in orientation, so we just take a single polarization direction of the field into account. Under this assumption, those fields can be described by a scalar vector potential A of t and x, and we are going to write down a system Lagrangian in the first step. And this first line here accounts for the energy contributions associated with the electric field and with the magnetic field. We then add dispersion by including polarization effects in the medium, and we do this by attaching harmonic oscillators psi to all points x of the medium, and we name their resonance frequency capital omega, and we couple those oscillators to the electric field in a dipole approximation with coupling strength little g. The model so far has been known for decades and is this famous Hopfield model, which yields the dispersion relation I had on the previous slide. And we added dissipation to this initially non-dissipative model by turning all those medium oscillators into damped oscillators. And we achieved this by coupling them to a scalar environment field phi, which we allow to propagate in some perpendicular psi direction, and this field can carry away energy and information. By assuming this field to propagate in psi direction only, we assume that this field has an anisotropic dispersion relation, but apart from that, it's just a 2 + 1 dimensional scalar field, and we couple this field in a dipole approximation once again to the medium polarization, so to the medium oscillators, and name the dissipation strength capital G. And this Lagrangian can be used to derive a consistent quantum mechanical treatment via canonical quantization, and one can then work out Heisenberg equations of motion, and they have surprisingly simple solutions. I just want to give you a brief idea on how this works, and therefore we will consider the equation of motion for the environment field. This field obeys this driven wave equation here, which has a source term involving the medium polarization, and the solution of this equation consists of two terms. We have one term here, which is a particular retarded solution of this full inhomogeneous wave equation, and we have a second contribution phi 0, which is the general solution of the corresponding homogeneous problem. And this phi 0 solution is basically a plane wave contribution to the field and can be interpreted as some incoming contribution to the field, which approaches the medium along the environmental direction psi and enters from this spatial infinity and has not interacted with the medium yet. And the remaining contribution is basically the scattering term contributing to this field. Using this formal solution, it's possible to decouple the remaining equations of motion for the quantum field operators, and it's then possible to derive a relatively simple solution for the vector potential. Although at first glance this might look a bit messy, it's actually pretty straightforward in structure. We integrate over wave numbers in x direction and have a second integration variable kappa, whose absolute value corresponds to the frequency of the respective field contribution here. We have operator-valued coefficients. Those bk kappas constitute the annihilation operators of incoming phi 0 photons, which are incident on the medium from the environmental coordinates direction. And we have a relatively messy but not too complicated prefactor. And it's possible to write down similar expressions also for the medium polarization field and for the environment field. And eventually, we can use those solutions to express the Hamiltonian of our model in terms of the annihilation and corresponding creation operators of those phi 0 photons. And it turns out that those operators diagonalize the system Hamiltonian, which is quite convenient. And the energy eigenvalues, rather unsurprisingly, correspond to the frequencies of the associated modes. in the vector potential. And that's all we need to know about the model for the moment. And we can now use this model to study the response of an inertial two-level particle detector moving at a constant velocity through a medium. This detector will later be realized with a hydrogen atom, and we assume it to be initially in some ground state, and we're interested in excitation probabilities to a higher lying state with an energy gap delta omega. We describe this full system via a Hamiltonian which is formulated in the rest frame of this moving atom or particle detector. The first term here just accounts for this detector's contribution. We have its energy eigenvalues and the projectors onto the corresponding eigenstates. The second term is basically just the Hamiltonian of the surrounding dispersive and dissipative field, compared with the Hamiltonian from the previous slide, where we had energy eigenvalues, absolute value of kappa. We now don't have the eigenenergies as seen by a laboratory frame observer, but have the Lorentz boosted energies as perceived by the moving detector. And we couple the detector's atomic dipole moment evaluated at the proper time of this detector to the electric field as seen by the detector along its world line at its proper time. So as usual, and I name this field E tilde henceforth, and it can be calculated by differentiating the vector potential along the world line of the particle with respect to the proper time. And within this model, it's possible to use the established procedure for calculating an excitation probability. And as usual in the treatment of Unruh-DeWitt type detectors, the excitation probability per time scales or is proportional to the Fourier transform of the two-point correlation of the field seen by the detector. And this temporal Fourier transform is to be evaluated at the detector's energy gap delta omega divided by a gamma factor. The electric field term here involves factors which are time harmonic functions. The same kind of function occurs here. We integrate over all times, so this integral will yield a Dirac delta function, and this Dirac delta imposes conservation of energy in the rest frame of our moving detector. It peaks whenever the detector's energy gap up to a sign matches the Lorentz boosted energy of one of the surrounding field modes. And since delta omega is positive, this condition can only be met for surrounding field modes whose phase velocities, absolute value kappa over k, are smaller than the absolute value of the atom speed. And this basically indicates that indeed those excitations which can occur rely on quantum vacuum fluctuations of the surrounding field, which move more slowly than the detector. Apart from this Dirac delta, there's another factor occurring in the two-point function, in this excitation probability. I just abbreviated this because it looks a bit messy, and just want to stress that this term is always positive. So if this term is always positive and this Dirac delta function always peaks somewhere, this suggests that the excitation probability should be non-zero for arbitrary atom speeds, so for arbitrarily slow detectors and for arbitrary dissipation strengths. But this observation is a bit surprising because apparently one would expect someone should have seen this kind of effect if it extended to arbitrarily slow detectors. And that's why we had a closer look at this term, and that's why I put it up once more here. And we are reconsidering this expression for a weakly dissipative medium with a relatively small dissipation strength. Whenever the dissipation strength is small, this prefactor here notably differs from zero only if the absolute value of kappa approximately matches one of those non-dissipative Hopf field energies from this dispersion relation I started with on my motivation slide. And if this condition is met, then the delta function peaks approximately where one of those energy bands intersects this expression here. And this expression corresponds to this blue line and has a slope which represents or reflects the atom's velocity. And for arbitrarily slow velocities, so for arbitrarily slow small slopes, there's always a point of intersection somewhere. But for very slow detectors, this point of intersection moves to very large wave numbers. And here one has to be careful, because at some point, the continuum limit approximation of our model will break down. So in a realistic medium, there are no infinitely large wave numbers close to the medium resonance. And this could lead to artifacts, and to avoid such artifacts, we truncated the wave number integral at a suitable cutoff Kmax. If we do so, it's clear that this point of intersection occurs below the cutoff only if the atom has a certain minimum velocity. So in fact, this Ginzburg effect does not extend to arbitrarily slow atoms. And one also has to take into account that a real beam of atoms would not be sent right through a dielectric bulk medium, but one would rather need to drill a hole through a crystal and send a beam of atoms through this hole. In this scenario, the atoms would not directly see the field modes in a bulk dielectric, but would rather see evanescent fields which leak from the crystal into the hole, and those modes fall off on relatively short length scales, so the atoms need to move very close to the surface to get excited. But we did an order of magnitude estimate where we envisioned a beam of hydrogen atoms in the 2s state, which is metastable, to pass through a hole in a block of silicon, and we found that spontaneous Ginzburg excitations should be feasible if the atoms have roughly a quarter of the speed of light and atom surface separations of roughly 9 nanometers. Meeting those requirements experimentally is definitely challenging, but should not be out of reach. And that's actually quite promising. So let me conclude with a few take-home messages. We considered a scenario where inertial atoms move through a dispersive medium and asked whether they can undergo spontaneous Ginzburg excitations. This question was inspired by the observation that close to medium resonances, phase velocities of quantum fluctuations grow relatively small, so might be smaller than atom speeds. In this parameter regime, dispersion and dissipation play a role. Therefore, I introduced a model for those properties, and we were then able to study inertial atoms moving through dispersive and dissipative dielectrics. We found that indeed those atoms can perceive Lorentz-boosted energies, which may grow negative, which could give rise to Ginzburg excitations, but in realistic media with a wave number cutoff, a certain minimum velocity has to be reached. And in a real experiment, this minimum velocity is on the order of a quarter of the speed of light, which makes such an experiment very challenging, but potentially feasible. And with that, thanks a lot for your attention.
Thank you, Sascha. Thanks a lot for the talk. I guess we already have a question from Morgan. So please, Morgan, go ahead.
Yeah, so this is really cool stuff, actually. I guess the first question is there an effective temperature? Like when you take the ratio of excitations to de-excitations and take the log of it, and you can get some effective temperature from that. Is there a temperature that you guys are looking for, or what would that logarithm thing look like for you guys?
We haven't looked at the temperature because we consider a scenario, anyway, the response would be really small. So we consider a scenario where we start with a very large beam of atoms, and just a tiny fraction of atoms sent through a hole will move close enough to the surface to have a chance to get excited. And then we would expect to obtain spontaneous excitations if we start with a very large particle accelerator at the beginning to produce a beam of sufficiently fast atoms. We would expect excitation events to occur on this order of every couple of minutes. Okay. So it would rather be an experiment where you try to see individual excitations.
I see. And then, okay, so these are neutral atoms, right?
Yeah.
And then I didn't see, so you had the delta function for the conservation of energy. And normally in Cherenkov radiation, you get the Cherenkov cone from that condition. Is there a cone that you get from these things, or is it emitted in all directions?
Well, the calculation I presented today was a one-dimensional toy model. Okay. And we included the three-dimensional estimates presented here rely on order of magnitude estimates, which are still a relatively simplified model. But of course, there you get some angular contributions. But in principle, the main contribution to this effect is of quantum vacuum fluctuations, which our detector overtakes. So I think if I remember correctly, the main contribution is from this particular parameter regime here. But that's a question that should be investigated more closely in a more realistic model.
Okay, and these are starting off in their ground state or the metastable state, right? So they're okay, and so you're looking for actual excitations.
Mm-hmm.
Okay, that's really cool.
And then by realizing a sufficiently long particle detector, one should be able to see the excited atoms to decay back to their ground state.
And
so this should
go ahead.
Should occur on some length scale. I think something like on the order of meter or something like that. So afterwards, the excited atoms should decay to the ground state, and we would be looking for the light emitted by this de-excitation process.
And I guess one final question, is because you had mentioned that you're working with an experimentalist. Are you guys actually building? I mean, is this an experiment that's in-house over there in Dresden or wherever you guys are? Or are you?
No. You really need a very large accelerator to produce a beam of atoms. So you start with protons from a large accelerator, and there you would need one of the pre-accelerators of those very large-scale facilities. So this experimental collaboration mainly intended to assessing, well, is this actually feasible in principle, but not aiming at a direct realization in the far future.
Okay.
In the soon future, sorry.
Cool. I guess that's, really interesting stuff, actually. I like it. Thank you very much.
So thanks for the question. Thanks for the answer, Sascha. So thank you again. And I guess that now we can go to the last speaker of the session, Patricia. Nice. Hello.
Hello? Can you hear me?
Yes, we can hear you. Let me just start by apologizing for having you as the last speaker. It's I was trying to coordinate the schedule because this is a very international thing, right? So I was trying to have like a reasonable time for everyone, and you happen to be right after Germany in the Netherlands, so it just happened to be exactly the cutoff for today. So apologies for that, but amazing. Okay, so okay, the next speaker of today is Patricia Ribes-Metidieri, and she's going to talk about entanglement in Minkowski spacetimes and the source of harvested entanglement. So please, Patricia, go ahead.
Okay, so thank you very much for giving me the opportunity to actually present this work here today. And this work is actually a work done in collaboration with a bunch of people, which you can see here. And well, let me just start with by telling you a statement that is probably well known in quantum field theory, and that is that entanglement is ubiquitous in quantum field theory. Even the simplest states of the simplest field theories are highly entangled. And from a formal perspective, we know that this statement rests on two different results. On the one hand, the Rindler theorem, which tells us that essentially, if we look at field variables in any one region of Minkowski spacetime, we find that they are entangled with field variables in any other region. And on the other hand, with something that has already been mentioned today, the calculation of entanglement entropy, which tell us that the entanglement between two adjoining regions in Minkowski spacetime is not just large, but UV divergent. And well, from a more, let's say, practical perspective, we also know that the entanglement in quantum field theory has to be sufficiently prevalent so that we can actually harvest it. And I will tell you more about it later. So, as I was saying, entanglement is ubiquitous in QFT. But one thing we can ask ourselves is, what does this statement mean in practice? And what I mean by that is that at the core of these two formal results I mentioned, so the Rindler theorem and entanglement entropy calculations, is the fact that quantum fields host infinitely many degrees of freedom, even when we look at regions of the quantum field that are confined in space. However, when we try to extract some observables out of this field, we do so using some kind of physical apparatus, right? Like the one that I have represented here, which are typically made of a finite number of pixels that have finite resolution. that I'm representing here with these arrows. So what I'm trying to say is that in practice, we can access a finite number of degrees of freedom of the field, which you can think of as being an average of the properties that each of these pixels can measure. So in this talk, I'm going to focus on two results that are kind of related and have to do with the following questions. The first one is how much entanglement is there available when we look at this kind of physically motivated systems with a finite number of degrees of freedom. And the second question is how is this entanglement distributed in practice? But before I try to answer these questions, let me just give you some more details of how we actually select these observables and how we measure entanglement between them. So let's consider a single degree of freedom of a scalar, the simplest possible theory you can think of. So free massless scalar field in Minkowski spacetime. And we are going to work in the canonical formulation. So then what I'm going to do is I'm going to select a compact region of Minkowski. And there I'm going to select a smearing function. And I'm going to use this smearing function to define the so-called smeared field and momentum operators, which are defined basically by averaging the field and momentum operator value distributions with a certain function, which you can think of as being the sensitivity of a one-pixel detector. We will also impose that this function is normalized such that these two operators satisfy canonical commutation relations. And with all this, we see that this pair of canonically conjugated operators, we say that it forms or constitutes a single degree of freedom of our field. But if we want to talk about entanglement, we need at least two of these subsystems, but we can proceed in the same way. So what we are going to do is we are going to select another compact region of spacetime, in this case, a space-like separated from the phase, and we can define another function, and we can use this function to define appropriate smeared observables out of it. So basically, we are extracting single degrees of freedom out of one region and another one out of this other region. So this approach has many advantages, among others that we are basically in the regime of quantum mechanics when we work like this, in the sense that the algebra generated by these smeared degrees of freedom is isomorphic to the algebra generated by a quantum mechanical system with two bosonic degrees of freedom. But there is a main difference. So in doing this kind of smearing procedure, we keep some degrees, we keep some physical information from the field theory. In particular, one important thing is that basically all reduced states that we can compute from this kind of field theory are with a finite number of degrees of freedom are mixed, which means that we cannot use entanglement entropy to quantify the entanglement between the degrees of freedom we extract from this region and this region. Instead, we are going to use logarithmic negativity. Okay. So regarding the first of the questions that I posed for this talk, the first thing we did was basically to try to answer how much entanglement is there between these kind of finite dimensional systems in Minkowski spacetime. So as the easiest thing we can ask, we try to compute entanglement between two such systems like this. So we extracted a single degree of freedom out of this red region, a single degree of freedom out of this gray region, that we consider for simplicity to be spheres separated by a certain distance. And in order to define the degrees of freedom here and here, we use a large family of different smearing functions. So a lot of functions that you can think of. And even some families of functions for which we could obtain analytic results. And the result we found was a bit startling at first, and is that for a large family of smearing functions, there is no entanglement between these two degrees of freedom. Which is, well, shocking at first, but not so much, right? Because the point is that here we just have just 2 degrees of freedom. So maybe these 2 degrees of freedom in general are not enough to capture the entanglement that lies in our quantum field theory. But we soon learned that this is actually something a bit more general, and even if we try to increase the number of degrees of freedom that we are analyzing in configurations such as this one, with tens, hundreds, or thousands of degrees of freedom is actually entanglement for this kind of finite dimensional systems is actually really hard to capture. Of course, this doesn't mean that there is no entanglement, and in fact, we can find entanglement in configurations such as this one, where we try to compute entanglement between degrees of freedom supported in the red regions and degrees of freedom supported in the gray regions. And we do find it, but again, it is actually difficult to capture, and we have to carefully fine-tune the parameters that we are using in order to do this. So then I'm bringing this up because, as I was mentioning, entanglement between a finite number of degrees of freedom in field theories doesn't seem to be as prevalent as we originally thought. And this is important because then we realized something that was also a surprise at first. And is that for typical modes that we can think of that Unruh-DeWitt detectors couple to, well, basically the entanglement that the detectors are harvesting cannot be coming from pairwise entanglement. But before telling you more about these kind of results, let me maybe summarize the kind of setup that I have in mind with telling you a little bit about entanglement harvesting. So in this setup, I'm considering two inertial detectors, A and B, that have a finite spatial profile. And I'm considering that, the detectors are switched on at a certain moment of time and for a finite period, this delta D here. And during this period, they are allowed to interact with a background quantum field, which I've represented with this background image. Now, during the time the detectors are interacting with the field, the interaction is of this sort for completeness, where, as you know, this lambda is the coupling, this mu describes the internal dynamics of the detectors, this psi here is the switching function, so how the detectors are turned on and off. And the important part is that the interaction between the detectors and the field happens through this kind of smeared operators at different times, where this function here represents the space-like profile of the detectors. Now, as you also know, we consider that the original state of the detectors and the field, so the total state, before the interaction is just a product state. And we know that under certain conditions after the interaction, we find that part of the entanglement of the field has been swapped into the detectors. Now, why I'm telling you this is because of the following observation. And it's that if we analyze carefully what the entanglement being harvested by the detectors is, we see that the only information that the detectors can actually capture from the fields is basically coming from these two families, continuous families of space-like smeared modes. And the result that I just mentioned is that now, if for completeness you want to select a single mode out of this family and any mode of this other family, and you try to compute entanglement between these two modes using the techniques that I described before, you will find that there is no entanglement. But there is no entanglement between these two, nor these two, nor these two, nor any other element of these two families. So, this was actually pretty shocking at first, because then we were asking, well, where is the harvested entanglement actually coming from? After all, if the detectors are able to become entangled, it's because they are being able to access some kind of reservoir of entanglement from the field. So then, of course, we realized that, the fact that there is no pairwise entanglement between these two families of modes doesn't mean that there is no entanglement at all. It just means that the distribution of the entanglement that the detectors are capturing is a bit more subtle. And in particular, it could be happening that there is some sort of multimode entanglement between all the modes in this family, with all the modes in this family, or just some subsets of them. So basically, this is our hypothesis that the detectors might be actually capturing multimode entanglement from these two families of modes. But how can we actually check whether this hypothesis is correct? Well, we decided to do so with doing a direct calculation. So this is what we did. First of all, we selected a discrete number of this family of modes that I was mentioning. along the time interval where the detectors are on, and such that the different modes are selected at uniformly distributed times. Now, these sort of modes look a little bit weird because, of course, we're in a canonical formulation, but just let me tell you that we can make sense of these elements as elements of the phase space at a reference time, in particular at the time when we turn on the detectors. And we can do so by using the inverse time evolution. So then, this means that we can use this procedure to define two families of n modes, one associated with each detector in the canonical formulation. The problem of using this procedure is that the resulting modes that we obtain through this are not independent from each other. So two consecutive modes like this one and this one do not commute. And you can see that by looking at this graph, at this figure, when I'm plotting the symplectic products of different, of field, momentum, and field momentum operators, or these kind of modes. And well, in principle, this is a problem because if the modes we are using are not independent, it's even difficult to define what we mean by multimodal entanglement and to define a proper canonical system. And in order to get an easy way out, what we did was to use these modes, as I defined, as a first step, and then we tried to orthogonalize them using a symplectic analog of the Gram-Schmidt algorithm that you probably are familiar with. So this is not completely straightforward, but once we did that, we ended up having two families of n modes, one associated with each detector, that are independent of each other and define a proper canonical system, which means that now we could compute the log negativity between the n modes associated with one detector and the n modes associated with the other detector by using just standard tools. So far so good. And let me tell you or advance the results, and it's that after quite a lot of, let's say, hard work, we could find multimodal entanglement. So let me show you what we found, and these are just preliminary results. So here what you are seeing is log negativity, which, as I mentioned, is an entanglement quantifier. By the way, a positive value of log negativity is a sufficient condition for entanglement in this situation, as a function of the number of modes that we are introducing for each detector. So the interesting thing here starts happening around here. So you see that if we get sufficient number of modes associated with each detector, we do find multimodal entanglement, even if there is no pairwise entanglement between any of these modes. And also, very interesting is to notice that here it seems that the log negativity is starting to reach a plateau. But of course, these, as I mentioned, are just preliminary results. And in order to confirm whether or not there is a plateau that would define the maximum entanglement between these two regions, we actually need to extend this plot here. But it is pretty hard to do that in practice. Let me also mention about this graph that we see here some kind of oscillations, which are simply related to the way we split a finite time interval into different ways. So this actually just matters when the number of modes is relatively small. So with this, I would like to give you my conclusions, which is that when we try to analyze entanglement between these kind of physically motivated systems with finite numbers of degrees of freedom, we know that entanglement is there, but it seems to be distributed in a subtle manner, and it is actually quite difficult to capture. In particular, we found that there is no pairwise entanglement between modes of the field that one typically uses for these kind of smeared Unruh-DeWitt detectors in the harvesting protocol. However, we also found that the entanglement that these detectors might be harvesting can come from a multimodal entanglement, between discrete sets of these modes, of these families of modes. However, a question that we still have to clarify is whether this is the primary mechanism or the primary source of the harvested entanglement that we measure in this protocol. So that's it. Thank you very much for your attention.
Thank you, Patricia.
Yeah.
Are there any questions from our Zoom audience? Well, while they come up with questions, let me ask you something then. So when you use the log negativity, as you mentioned, it's true that log negativity is sufficient for confirming that there is entanglement, right? However, it's not a faithful entanglement quantifier unless you are in systems of bipartite systems of qubits or a qubit and a qubit, whatever, something like that. So up to which extent can you really claim that there is no entanglement, like between the different pairs, in the sense that you're not really using a faithful entanglement quantifier? Could you talk a little bit about that?
Actually, yes, of course. And actually, the nice thing about this log negativity is that it is faithful in systems when we try to measure entanglement in systems of 1 versus n modes, right? So in this kind of situation, when I was analyzing pairwise entanglement is actually a faithful entanglement measure. It is not a faithful entanglement measure in the sense that it is only sufficient when we look at this situation and we try to analyze multimode entanglement. But then, as I said, still in this case, we do manage to get some log negativity. And then we can conclude safely that there is entanglement in the system.
Amazing. Thank you so much for your answer. Are there any other questions from the Zoom chat, from the Zoom audience? I don't think so. So in that case, let's thank Patricia again. Thank you so much for the presentation. And now with this, we had our last speaker. So I'd like to thank all of the speakers of today, everyone that has presented here. That was definitely a very nice showcase of the different kind of RQI research being done throughout the world. We started this thing in Japan and we ended up in the Netherlands. And then next Friday, at a completely different time, we will have the RQI Circuit Online, the second edition, for folks that are mostly on the West. And I hope to see you there. So right now I'll stop this